afternoon, ladies and gentlemen. My name is Melinda. On behalf of FOSI committee, it is my pleasure to welcome you here today in FOSI online talk series. I hope you enjoy your lunch already and ready to hear the presentation from Peter Lunt. Amid this COVID-19 outbreak situation, hope everybody doing well, stay at home and keep physical distancing. I would like to extend my gratitude to our sponsors of Noble Energy Resources and Geoscience Delta Andalan for funding of this Zoom platform. So with us together, already joined Mas Reiki, the General Secretary of FOSI, Pak Herman, our advisor, Pak Win is our advisor as well. The rest will joining us soon. So we're glad to inform you that we established the FOSI YouTube channel. We uploaded all the videos from previous talk already. Don't forget to subscribe and like the channel, and please enjoy the video. And for sure, today's talk will be uploaded as well. So I would like to thank you for joining us today for this special presentation on Southeast Asian stratigraphy at a large scale, hunting the next generation of plates and new plate tectonic models. The registered participants is 280 plus. Get ready to be excited. The presentation will cover the height curve, large-scale stratigraphy controlling factor. The new method will be shared, including its examples in Indonesia. So moving right along, it is now my pleasure to introduce our guest speaker. Really honored to have Peter Lunt. Currently, he is an advisor at STRATOS Energy in Kuala Lumpur and a young lecturer in stratigraphy UTP Malaysia and Kian LM Kindau. Many thanks for sparing your time in weekend with us, Peter. Okay, I believe most of you know him very well already, met him, or maybe already have his useful publication on Indonesia stratigraphy. So, well, before I hand over to Peter, please allow me to give you some rules in order to make this meeting running smoothly. I would like to get your attention for a moment. I recommend all participants to mute the audio and switch off your video during explanation from presenter to maintain a good connection. Second, the presentation may be recorded for screening within the FOSI platforms. Last but not least, a Q&A box can be found in the icons panel, usually at the bottom of your screen. Enter your name for the committee to collect after the presentation. It will be entered live later on by Peter, and you might turn on your audio or video to deliver your question to Peter Lunt. Well, ladies and gentlemen, enjoy the talk and please welcome Peter Lunt. So, Peter, this is your turn.
Right, thank you, Melinda, for that introduction. Okay, a slightly unusual title, especially the mention of the large scale, and this follows on from what I hope most people will have done last week and seen Bob Morley's presentation. As Melinda mentioned, I have been publishing for some time on Java in Indonesia, and I'm actually going through a bit of a flurry in publishing at the moment, so some of the ideas I'm going to show you today either in press or are just about to be submitted. What we're trying to do, as the title tell you, and the hunting the next generation of plays and new plate tectonic models, is quite an ambitious attempt to turn around the way we do stratigraphy in Southeast Asia. Anybody who knows me, Herman, Maslan, they know that I've been quite keen on this for some time because I think Southeast Asia should be leading in this, not following. We had imported passive margin models for a long time, and I think we need to break away from those and develop new models that we can develop here and possibly even export, but certainly better explain the geology in this part of the world. Yep. And there we go, second curve. Okay, quickly the topics to be covered. I do want to go into the hack curve. Bob mentioned this last week. That'll come up in a few slides. Some points to mention here. This word deductive stratigraphy. I'll explain this in a moment. Just bear in mind it's an important part. So I want to go why the hack curve, which we still religiously put on our diagrams when we're doing stratigraphic summaries, why it simply doesn't work in Southeast Asia. And very quickly, what does control large-scale stratigraphy in the region, which in one word is tectonism. The new method, though, is quite different, though. It's inductive and evidence-based. Deductive and inductive are not quite opposite, but they're quite different ways to approach logical problems, and I shall go through this in a few slides, because this really does turn around how we do our work in Southeast Asia. And I won't spend a huge amount of time on stratigraphic theory, and I'll go straight into examples, how this impacts our understanding of basins, what are basins, provinces, plays, petroleum systems, and even towards the end, tectonic ideas. And hopefully Chris Moll is tuned in from PTTP and Chiang Mai University, because I've been having a lively discussion with him on how to integrate stratigraphy with tectonic models. And I think a change is long overdue for all of these factors. Okay, just to announce that FOSI has a copy of this presentation. If you ask nicely, they'll give you a copy. So you don't need to take screen grabs or photographs of the screen. If you want any of this, you can just ask Melinda and she can provide you a copy. It's quite a big file. But what I want to do is get these ideas out there for discussion. It's all based on published data, stuff that may not be published just yet, but it's got permission. So it's all open file data. I really want to start a discussion with people to say, look, if we are going to change the way we work, where's it going to go? So last week, excellent talk from Bob Morley, and he went through his latest work in what he calls the VIM scheme, Vietnam, Indonesia, Malaysia. And he was saying there's no evidence for the hack type use signature in Southeast Asia, which I think most people working here for some time will know that they can't really apply the hack model. They can force it onto the seismic interpretations, they can apply some of the terminology, but it isn't predictive. And that's one of the problems. We've stagnated a little bit. So I've been looking at that larger scale signature and done a lot of research on it, which requires looking not only at weld age, and I've been around, as I was saying at the introduction, for about 35 years. I've seen most of the basins, been through a lot of the well reports. I've read a lot of the, the field mapping guides, and we can now explain those in a tectonic framework. And that then knocks on to the scale of things that most geologists are concerned about, which are plays, risking of plays, and petroleum systems. What has come out of this is a criticism of, I think, of the basic plate tectonic framework, which is quite interesting. Not of immediate exploration importance, but it's the sort of foundation on which we base our ideas. So I'd like to say this is a time of optimism. It's unparalleled opportunity, both for exploration and research. We have stagnated a little bit. I think it's time we can move forward, find new plays, and come up with some very interesting new ideas for the geology of the region. Okay, this is a quick summary of Bob's publication. It might be slightly out of date. This is 2015. He did with Tony Siswiski. The grey bars that should have flicked across your screen, they're the scale of what I'm looking at. So it's not quite an order of magnitude. It's a much bigger scale than what Bob looking at. So Bob has developed this VIM high resolution correlation scheme that works apparently very well. He's spent several years developing and refining this. I'm not going to contradict anything he says because I'm looking at a different scale. And again, I've been integrating outcrop data where you can't really apply VIM. It's very hard to get continuous outcrop to apply VIM stratigraphy. I've had to use different methods and different techniques because I'm working at a different scale. So this follows on from Bob's work, and hopefully I don't contradict him anywhere. But it's just putting some perspective for people who aren't stratigraphers that basically I'm looking at a slightly different data set to what Bob was looking at. So, okay, this is a standard slide, and I put that little disclaimer in italics. Basically, the VIM scheme is looking at a high resolution correlation. I've had discussions with some friends of mine about these first, second, third order sequences. You see many papers titled the third order sequences, and of course we're all familiar with the TB 2.1, 2.2 third order sequence units that are banded around. I don't believe they occur in this part of the world. After 30 years of looking, I've seen no evidence for them. What we do see is a different system. So again, why not use to see at that scale? And the reason is quite simple. The foundation of the static model said it wouldn't work here. You have a copy of the big red SEPM volume. I've got publication 42. Big chapter by Henry Possamentier and others. This is actually scanned over 2 pages. There's a break somewhere in there I've had to take out. But before they go into their lengthy discussions of the hack type sequences and how you interpret seismic and sequences accordingly, they quite wisely put these caveats in. And it starts at the top there, hopefully you can read. It was assumed that the following conditions would be present. Well, I've highlighted in yellow things that simply don't occur in Southeast Asia. Anybody who's worked here can very quickly say this isn't true. For instance, seafloor subsidence is primarily a function of the atmospheric cooling. Well, no, we have rifting, we have mobile rifting, it moves around, sediment loading, sediment supply changes. They claim geohistory analysis supports that idea. Well, If you actually do geohistory in Southeast Asia, it shows the opposite. Total subsidence in the basin with direction, so you have a constant proximal to distal dimension. I'll show you an example in just a moment where this clearly doesn't apply. And in fact, in most basins, maybe you could argue that the Kutai Basin, the big Mahakam Delta, is a single proximal to distal direction through time, but most basins aren't like that. They assume that the eustatic change is curvilinear approaching sinusoidal. Well, I think Bob is seeing a little bit of that at the fine scale, but on a large scale, it's not. You can have a transgression followed by a bigger transgression. But basically, we're applying the wrong method here. But this became so popular globally in the 90s and noughties that basically it dominated our thinking. And at the bottom, they quite wisely say the overprint of local factors must be considered. We have everything dominated by local factors, and we have to make a model based on local factors. And we've been a bit lazy in doing this. Analysis are now a small part of research and analytical budgets, and we've lost the tools to actually criticize these deductive models. So I've been looking at that and sort of comparing and contrasting, and then showing a little bit about how the new model is pointing at new plays and new plate tectonic models. A very good example, but by no means unique, is the Sarawak-Lakonia area of Malaysia, the Baram Delta up here, the MLNG refinery somewhere down here. But you're very familiar with these provinces being named. I think Maslan had a hand in defining and going through these province names, but they've arisen over the years because each area's got its own unique stratigraphy. Central Laconia is the area we have the big Laconia reefs. They disappear to the north in North Laconia, and they disappear to the south. So each area is not a depicenter as such, it's an area with a unique stratigraphy. But this area is quite good for illustrating a principle that basically we don't have the conditions required by Parmentier and Vail and all the other workers from the Exxon school. Okay, these black and white maps were published by Charles Hutchison in 2005, but they've been around in the industry since Shell in the 80s, and Petronas also refined their version. They're all very similar, and starting here on the lower left, we have the later Oligocene. I would draw these slightly differently, but these still show a message that in the later Oligocene, sediment was coming somewhere in the southwest, heading towards the northeast. So that's your proximal distal dimension. These maps are based on, I remember that in those days, seismic was 2D, and it was obviously getting better, but it's still not like today's quality. So these maps were really based on the facies present in the wells, the microfossils, the log signature, sand, shale ratios. But clearly, they are seeing basically this proximal distal direction. This is basically on the cycle 1 to 2 boundary. I'll come back to Sarawak briefly later on. But this change here is due to a regional tectonic event, the base Miocene unconformity. If we go into mid-cycle 3 in the lower, they're using the ultimately lower to middle, early to middle Miocene, you're starting to see the sedimentary system rotating. And by the time we get to this point here, it has rotated through 90 degrees quite quickly. So now the basin is facing perpendicular to where it was just a few million years before. That is not really acceptable under the Parmentier scheme of things. They want a constant passive margin proximal and distal direction. But also in Sarawak, we know we're getting faulting occurring at the base of cycle 3. Base of cycle 4, we're getting major faulting, then accelerated deepening in cycle 5. So all of these changes help define what were the cycles of Sarawak. I'll come back to briefly later on. But this set of diagrams simply shows that over time, all the conditions mentioned on that first slide for Sarawak were not met. Basin subsidence was controlled by tectonism, either by basin uplift of central Borneo, changing sediment supply, or the opening of what's called a Bungaran Trough up on this west side over here. So you can predict from their own definitions that the third order scale eustatic model will not apply to Sarawak. And yet for 20 years, companies were trying to do this. And of course it wasn't working, it wasn't being predictive. They were just giving what in the 1970s had been given color names for seismic arise, and they just gave arbitrary TB names to. And this was all predictable under the Exxon model. And just to stress, Sarawak is just one example. It's nice because it's got that rotation through 90 degrees, but people are familiar with my work in East Java, or all of Java. That definitely is very complex, and I'll show some examples of that. And I've lost my screen. hang on a second. I hope that interruption didn't affect you. I think it's just on my computer. Okay, but again, even relatively simple basins of Western Tuna and the Malay to Patani basins have episodic stages of development that tie to regional plate changes. And East Indonesia, of course, is far more complex. We can't claim to try and understand East Indonesia until we understand the more simple Western side. But there clearly, I joined Petram a trend in the mid-1980s, looking at the Salawati Basin, which is something, so basically it's a Pliocene to very latest Miocene basin. So that's 5 million years containing 5 kilometers of sediment. So again, East Indonesia is an order of complexity more difficult. But basically, we were trying for a long time to apply passive margin models imported from the Atlantic margin. And the worst thing was we were applying them in what's called the deductive way. And I'll go through that in a few slides because it's this process of how we rationalize data that's quite critical. There's nothing wrong with the Exxon model, as far as I know, for the Atlantic margin, but not in Southeast Asia. Now, one thing I want to stress is this Mulu well up in North Laconia. It's a wonderful example, just to illustrate the control that tectonics have. And this, by the way, is the Bungaran Trough. It's also known as West Laconia Basin. Bungaran Trough because it is a fault-controlled elongate low like that. So Mulu up in the north is a wonderful, wonderful example. And what I've done in this, I think it's about 90 slides, but if you want to take out 2 slides to summarize it, this little set of 3 or 4 with animation, plus one later one, capture the whole topic of what I'm trying to get across here. Now, the Mulu one was published, it was in the Petronas 1999 book. Maslan has again republished it on 2013. Last year, I got permission to publish it again, just tagging on this basal part at the bottom. This was from a nearby well that was drilled 2016. I've forgotten if it was the paper I put it in said which well it was. I better not mention now, but same fault block, but it went that bit deeper, and that was crucial. But just to remind me here, geohistory diagrams. I'm sure a lot of you saw Doug Waple's talk a few weeks ago. This again emphasizes the importance of geohistory. Now, this differs from what he was showing. He was showing a lot of worldwide examples covering large time intervals. Southeast Asia, we get good age dating because we are tropical. We've got good zonations in the Cenozoic here. But it's a different scale of looking at the problem. And we also get some pretty extreme uplift and subsidence. And these sort of diagrams are wonderful for showing that. So hopefully with this set of diagrams, I'll really bring home this importance. This annotation on the side is not really critical, but basically for a long time, people didn't know where to pick the cycle 1, cycle 2 boundary in the area. Now we have this deeper well, we know it's down here. Let me go to a slightly cleaner version. Okay, now just some background. We know from magnetic anomalies that the onset of plate drift in the South China Sea was about 24 million years. I won't go into the pedantic detail of that. Sometimes they say 25, but that's a slight old version of the magnetic anomalies. Then, of course, we had the major risk subsidence of the Bungaran Trough at about 16 million years, and these were huge events. So they're the 2 controlling events. So basically, to go in a historical frame, at the bottom we've got coals. Now, these are in several wells that go this deep. Have bedded coals, non-marine. There's no marine fossils except stuff that caves down. Any sidewall cores lack any sort of fossil indicators apart from palanomorphs, and the coals are bedded. You see them on the wireline logs. So this was deposited at sea level, maybe slightly above sea level, back in the Oligocene. Markers like Mayopolis and Architensis and other things down there clearly date this. So there's your first interesting point. 5 kilometers depth below sea level in North Laconia now, we have bedded coals. That's quite a subsidence. What I'm saying is it's not just one subsidence, it happens twice. The good control on this is it drops down. I've drawn what they call a Mackenzie rift subsidence profile. Mackenzie was a structural geologist looking at plate tectonics and the rifting sequences. And basically a simple analog is when the rifting goes to drifting, you get a rapid subsidence then sags. So that's why it's not a straight line. I've assumed it's a rift subsidence profile, but it doesn't make a huge difference. Because what we know is that went from being at sea level to receive bathyal clays. We know this from the TD of Mulu and other wells. But it created this accommodation space. And I put very limited decompaction on these diagrams. You can play around with that. And again, it doesn't make a lot of difference. We have to make this accommodation space because we fill it with nearly 2 kilometers of sediment to get back to sea level. So that's the first step in subsidence. It's quite dramatic. We know it has gone back to sea level because basically in this area, not at Mulu, but a few kilometers away, there are a few small reefs on seismic growing over this unconformable surface at the transition. These have been confirmed by drilling. They're seen on seismic, they have been confirmed. I'll show them in a second. So basically, at some point about 24 million years, the bottom dropped out of this area. Beds that were coaly were directly overlain by bathyal clays. Sedimentary input into this area is quite high and it filled back to sea level. The samples from this top section before the doused MMU are shallow marine and neritic. Very sharp contact. In this location, it's overlain by hemipelagic chalks, elsewhere a reef. Well, the very fact you get this reef nearby on the same horse block that's now 3 kilometers below sea level says that, right, the second event also has dramatic subsidence for that reef that was at sea level to now be 3 kilometers below sea level. So this geohistory diagram is really good because it shows well-constrained creation of accommodation space. You can't really argue with this. You can play a little bit with the ages, you can dispute a few things like that, but overall, 2 major steps. This area collapsed. There's no other word for it. And of course, now the sediment's filled to its depth here, just over a kilometer where the Mulu well was drilled, but it's all pretty deep out there. This is the key part. On the top of my geohistory diagram, I draw the hack. It's actually the hack in Kaltani 2005 on lap curve because that was done to the same time scale that I do on my data too. So basically, you look at things like the Middle-Oligocene sea level fall, and again, Bob was saying that he doesn't really see this signature. He sees used to see, but he doesn't see this signature, the hack signature. I'm saying, okay, at a small scale, you might have eustatic variation, but look at what's controlling geology here. It's a scale of magnitude bigger than the hack curve. So that's the first of 2 slides you want to take away. Basically, is this massive 2 clean breaks where the bottom drops out of this area. Yes, this is an unusually good area to show this in, but I'll show you other examples from North Sumatra. I haven't got any Makassar examples in this talk, but it happens there too. And this fades away from the axis of rifting, but it just shows what controls the geology. The basin readjusts, the basin changes shape, the sediment supply changes, and it's all controlled by tectonics. And you can't see something as small and as minuscule as a hack curve here. So why are we using this as a guide and a predictive tool for our geology? So the Mulu is really important because it drives that home unequivocally. There's no way you can argue about this. This is out of Hutchison, 2004. It got reproduced in his book, 2005. Since then, they've actually drilled, this looks like a tiny pimple, but actually it's actually shown to be a little bit bigger, and it was drilled Tuntong well in 2015, so it confirmed the reef was there on this horst block. So again, we're getting these units, this first boundary. These are dates given to it by Charles Hutchison. I'd correct those now, but I haven't wanted to change his diagram. So you get the first unit ending here, the second unit ending here. And this is what they call a buried topography unconformity. I'm not sure these faults really do that. That's pretty clearly at the end of that topography. Bit of a hiatus when the condensed chalks were laying down and the main classics came in over the top. Even after the well was drilled, Mulu was 1994. 1995-96, a major oil company, I shall not name, you can probably all guess who it is, still wanted to apply the hack curve to this part of the well. Even though they had results from the Mulu well in, they're still seeing what they wanted to see. And these are basically, they've even got this base of TB 1.1, the 30 million year event, which nobody has seen anywhere in Southeast Asia. Again, I'll go into a bit more later on. So they were basically forcing on a model that simply does not work here. And that's been the story of geology, sedimentary geology in Southeast Asia for 20 years. We have to throw that off and start again. Now, an important part about these unconformities, and I'll go through this a little bit. I don't want to turn into a lecture on stratigraphic theory. These unconformities have properties that can be mapped. They must obey implications from Walther's law. There must be a pattern to how they stack up and facies change. So people haven't really done this. They haven't been tracing unconformities. The point here is this is a base Miocene unconformity, which is a huge event all around Sunderland. It's actually reasonably easy to date, and I'll come back to this on several examples. It's on the Oligomycete boundary. There's a clue, lots of markers there. And it has a lot of character changes, and it's widespread. This second event is what I call the doused MMU, because the term MMU is too widely used. I always qualify. This is the one that Harry Dowse defined, one of the earliest ones. That's very much focused in the West South China Sea, and it's not really seen anywhere else. So these unconformities have geographies, variations, and we haven't really been tracing those and following them, because that ties directly to the tectonic history, makes a predictable model that we can use for exploring and finding new plays. So there's a quick introduction. Hopefully I've demolished anybody's faith in the hat curve. I've got a lot more. This is just a potted version, but basically I keep on mentioning this 30 million year event. It was mentioned in questions last week. I've looked at a lot of mid-Oligocene sections. I've done field work of continuous mid-Oligocene sections. I've seen no evidence for it here. So if that's the biggest event on the hat curve, it simply ain't found in Southeast Asia. So what chance do we have in finding the other smaller events? Okay, I'm going to go through some methods. So I didn't want to turn it into a lecture on stratigraphic principles, because for a lot of people that would be a little bit difficult. And it is a bit abstract in places too. But I highly recommend the work of Ashton Embry. He's Canadian, along with Andrew Mile, two very good researchers, both approaching retirement, but very, very good workers. This paper he did with Erik Johansson, I've never met or talked to, emailed, but that's 2017. Very, very good paper on stratigraphic principles, because it gives both sides of the argument, both inductive and deductive. He's gone down, for a lot of cases, down the inductive route, i.e. building a model based on evidence rather than assuming a perfect example. And he's come up with this principle of episodic tectonics. And this is a paper published now 2 years ago. This is a bit specialized. It shows us similar principles to what we're trying to do in Southeast Asia, but in the Canadian high Arctic. But basically, this is something they've been developing, and it really applies to Southeast Asia. So this terms inductive and deductive I've been mentioning, very important variations on how we approach work. Deductive logic, you've all heard Sherlock Holmes deducing things. He's not actually, he's inducing, but deductive apparently sounds better. You have a paradigm, you have an ideal model, you have an observation, and you derive based on the observation compared to the ideal paradigm. So you're deducing, pulling down from something. Inductive work is Baconian. Basically, you make observations, you look for pattern, you make a hypothesis, you test the hypothesis, and you go back and you do it all over again. It's building from evidence upwards. They don't really go in parallel. You can step between the two different stages. Again, this is going down a route I don't want to go to, but there are different ways of handling data. Deductive process is very simple, but you can have good and bad deductive interpretation. Here's one I pull off the internet: all oranges are fruit. That's your paradigm. Fruit grows on trees, observation, therefore oranges grow on trees. And then you think, well, what about strawberries? So you can quibble about the word all here. Not all fruit grows on trees, but this is the ideal, and you deduce down from an ideal case to an observation. Here's a much simpler version. But the main thing is it's deriving. It's a very simple process, and it often gives rigorous proofs, but it's very poor at projecting. It's very poor at making extrapolations. The model we've been applying to our seismic and stratigraphic studies for 20 years are deductive. This is a diagram you've probably all seen showing the different generations of sequence stratigraphy. What you probably don't realize is that all these first four are deductive. You have the idealized, what they call a slug model that was developed out of the Exxon group, that strange cliniform shape, the ideal shape of a cliniform that goes through a low stand, then turns around to a transgressive systems track, develops into a high stand, sea level drops down again. That's the ideal model, and they deduce what you see on seismic compared to that. And you say, ah, this is a transgressive systems tract based on a comparison to the ideal. What Curry, Embry early on, Embry 95 is another good paper, and also the Embry and Johansson, which is a very good paper, simplified, a lot less divisions, because they're saying, no, base it on data. A lot of these features, these bold lines of sequence boundaries or maximum flirting surfaces, you have to interpolate on seismic. You force them through, to put it crudely. And Ashnob has never been keen on that, so a lot of your seismic ends up being interpretation rather than observation. His method of looking here for the maximum regressive surface you observe. So he's reducing it back to what you actually see, and therefore you're not compounding assumptions. The advantage to an inductive system is it does have a better capability, and it can be wrong. A good deductive system is never wrong. It's a logical flow. You induce and project, and then you test it. But you become a system that basically the word induce means to lead or to show towards. You can extrapolate a geological system. The kind of complexity we have in Southeast Asia we're all familiar with means you cannot use these deductive models because the ideal, as I said in those first few slides, doesn't work. It doesn't apply. There's too many exceptions. If you build a model based on this system, it requires a bit more time to begin with, but you come up with a model that is actually genuinely predictive. And this is what was happening in Southeast Asia in the 1970s and early 80s. And Shell in Sarawak with their cycles, unfortunately named. They expected something, but they ended up with a tectonic system. I'll come back to that later. But they kept the name of cycles, which is not really appropriate. And you had the Chinese mapping in the South China Sea, their T horizons. BP did work in Vietnam and East Java using, again, T for mega sequences based on their boundaries they observed. So people were doing this kind of work. But when the Exxon school came through in the 1990s, basically it was all put on the sidelines and ignored. And I think it's time to resurrect some of that old quality work. Here's a famous cartoon you've probably all seen, but in a slightly different context. The elephant, I think it's the poem about men of Hindustan. But basically what these people are all doing there, deducing from one piece of observation a conclusion. What you have with a deductive method, you've got a library of known shapes, known species, or a theoretical ideal like the slug cliniform, and based on a most similar principle, you deduce what you have. You are pulling down from this ideal model. But if we're saying that that ideal model isn't appropriate, you're going to be coming to the wrong conclusions. So the logical method is almost guaranteed to fail when dealing with new or unique objects. In Southeast Asia, you know you're going to be dealing with some slightly unusual basins. One of the strangest basins is, it's termed a Tarakan Basin. It's actually a cluster of different basins with a complex history. You need an inductive method to sort that out. It's far too complicated to assume you know what's going on and just color it in accordingly. Now, this is the second key slide. And this is the problem we've had. The deductive process has more easily planned workflows. You load your seismic, you start interpreting it, looking for those high stands, the on-lap surfaces, all these type of things. You start drawing it up, in your mind. And it's normally easy to plan a project and achieve a result by a deadline, because basically at the back of your mind, you think you know the answer. It's in the ideal model. You just haven't located it in this study area yet. And that's a bad workflow. Managers like this kind of work because they can draw up Gantt charts, they can tell their boss they're 30% complete. It's more easy to manage, and this is quite understandable. It's not their fault. But if you want to find reserves off the creaming curve, which until the oil price starts going up to $140 again, the creaming curve doesn't make sense. You've got to find stuff off the creaming curve. Or if you want to make important scientific advances, you have to argue and design a project that does not go down this deductive pathway. Because basically, other forces will try and design a project that's easy to manage that will finish on time with product. So again, you have to fight to get a project done that will look for something new. And to repeat, the deductive methods have got very limited predictive ability. I didn't go off on a long example, but I think the examples I've shown you show that basically if you're assuming things, you've already assumed you've got an all-encompassing theory for your basin, when in fact you haven't, and you're not looking at the exceptions that test the rule. So it's not good for research, and it's not good for finding the next generation of plays. And let's be blunt, there have been very few things that can be considered new plays in Southeast Asia in the last 20 years. I think we've been held back by this deductive approach. Once we break free of it, there's a very good chance we'll find whole new plays. I think we've found some already. I'm sure there's a lot more we haven't found. And I think there are a lot of interesting tectonic and other geological correlates coming out of this. So I think it's a very key point to make. But you've got to argue for a project, design a project, and get management support for a project that doesn't just do like the last one they did for Brazil or for some other country which is passive. You've got to design something that's specially adapted to Southeast Asia. Because basically, this, as I said in this paragraph here, the deductive methods, the Vail hat curve, does not predict the Laconia reefs of Sarawak, which have produced 3, 4 TCF of gas. I don't know. I've lost track. It must be more than that. The delta of the Kutai Basin was turned on at some point. It wasn't always there. The Aran supergiant gas field, which is gets like 14 TCF of gas and 500 million barrels of condensate, that doesn't fit the deductive model. Banyu Europe, I'll talk about. Jatibang in West Java, not in this talk. A whole bunch of important discoveries would not have been seen by the deductive method. Now, the reefs obviously stand out on seismic, but simply the presence in Laconia reefs is not predicted. In fact, I think the next slide shows this. So the Laconia model here, the Laconia reefs were turned on quite quickly. They were interrupted at one point, cycle 4, cycle 5 boundary. And I'm just publishing now why I think they demised, most of them, not all of them demised at about 8 million years because of an event like this. And that's different to what's happening in East Java. This is from Brands and Matthews, 1995, very good paper, where by chance the Pupu or the Kudrun limestone where it's reefall, this is actually things like BD and Madura Straits, most of the reefs of this age, actually correlates in age to Subis almost exactly, 24 million years to 20 million years on strontium and microfossils. So getting these correlation of events that simply would not have been predicted by these deductive sequence stratigraphic methods. So if you want to find more plays that have either reservoir or source that are controlled by these, you've got to drop the deductive approach. The difficulties of the inductive approach, the opposite, is it's a building process. And you're never quite sure what mistakes you're going to find, where the next step's going to take you. So it is hard to design a project. It's best if you've got 30 years of experience, because I know which wells you want to look at, where you want to go. But there are all sorts of opportunities to say, look at new areas. I have a whole set of presentations on this. I can show people for things being overlooked. Some I think have got potential. That's a separate talk. An important point now in a few slides, for stratigraphy, an important point in building a new model is the application of Walther's law. I keep on going, anybody who knows me know I keep on going about this, but this is like in physics. You've got 4 laws of thermodynamics, about entropy, work being transfer of energy, and then there's 3 laws of motion, action, reaction. They can all be reduced to 1 or 2 sentences. Walther's law is the same fundamental. If you, and I've seen so many cross sections and reconstructions that break Walther's law, you can't. It's like having a perpetual motion machine in physics. It can't be done. So you have to apply Walther's laws. You're developing a new model. You have to apply Walther's law to test your ideas. So that's one really good constraint. And I'll show you some examples of this. Leading to the first actual example. We're used to thinking about unconformities based on their geometries. Most of the terminology we have relates to angular, erosion, all the terminology based on geometry. The top diagram is sort of putting color in for facies. And facies is based on a whole bunch of things. Microfossils are very important, but also mineralogy like glauconite, siderite, coal beds. And you often see a jump over these unconformities, even when they're not really apparent on seismic. I won't go through this word for word, but basically unconformities are where to scale of observation Walther's law breaks down. But as I'm trying to argue some of the papers in press, when you look at a larger scale, the unconformity, as long as you're in a congeneric sedimentary succession, so you actually have fading to power conformities, those unconformities, so the Sikar point wouldn't, but anything within Southeast Asia that covers a few 100,000 kilometers will fade out, but it'll have properties that at a larger scale are still governed by Walther's law. I need to show you a lot of examples to get that message across. Hopefully those will come up in the next few slides. But this is quite a complex point, but it really is quite important. Just think about it this way. If you're a reservoir engineer looking at a core, something a scale of meters to tens of meters, and you see an unconformity, a big one for your scale of view. When you're a regional geologist, you may not even see that on seismic. A regional geologist doing your ventures over the same field with that small unconformity in, you go up an order of scale, that unconformity gets absorbed into something that still has prediction under Walther's law. So what I've been doing around Southeast Asia is tracing these unconformities, making sure they're dated and correlated, and mapping the facies contrast above them and coming up with a bigger picture. Oh yes, this is something I've come up with after all these years. My background is in micropaleontology, where there's a famous quote that applies because we're looking at things that are millimeters or less, and of course most of paleontology is published on dinosaurs and boring metazoans. G.G. Simpson, a famous paleontologist, came up with this quip that size is the most important property of an organism. And the more you think about it, the more it's relevant. You know, ants can fall off their desk onto the floor, turn over and walk away. An elephant can't do the same thing because size is critically important, gravity, surface tension. So people overlook this because they're looking at all these exotic features that insects have or birds have, but size is fundamentally important to organisms. I believe size is the most important property of an unconformity. And I think that'll come up in the next few slides. Now I use this term non-Waltherian contact. And this is my very broad definition of an unconformity, including the places where it's conformable. A correlative conformity or paraconformity or non-conformity, again, lots of words, but you see a contrast in the facies. And again, you have to look at other things. You have to do analytical work. On seismic, you may see absolutely nothing. And that's what this example will show you. But in terms of facies, you see something quite major. This can be a very large area for the unconformity surface. Not all the unconformities are easy to spot on seismic. So non-Waltherian contacts are basically where you see this jump in facies. And often you can trace that to a plot unconformity somewhere else. This example hasn't been published, so I can't tell you where it's from, but it's a really good summary because you see this first on label number 2. This shallow unconformity is really quite distinct. But actually in this well, at exactly this point, there's a massive change like this, where the change in facies is huge, where you get something that's fluvial to coastal, something that's very deep marine throughout. And the set casing here, so it's good control. I had sidewall cores. The log signature doesn't really show any major change. You can see coarsening up, coarsening up, coarsening up. It's only when they're doing analytical work you see this major jump. And in fact, regionally, it's this deep unconformity that's more important. The shallow one is more local. But this is a very good example of a non-Waltherian contact that really the average geologist coloring in logs and seismic would overlook. You must have the analytical data to see this. By recognizing these and tracking them across a large area, a very new picture of geology for Southeast Asia comes out. Falling a bit behind schedule, so I'll try and skip forwards a little bit. Basically, this is a slug model. I want to go on to this type of contrast here, which is a massive contrast between basically something that's, like in the previous diagram, something that's fluvial to coastal overlain by something that's bathyal. As I say, these slides are available, but I'm already a little bit behind. Let me just skip over those, how it changes. These are quite common around the region, as you'll find out in the next few slides, and they've generally been overlooked or underappreciated. Geohistory analysis is very important in illustrating the magnitude of these. Oh yes, and a quick point here, it's quite important considering our current situation. We're trying to do a little bit of an about turn in the paradigm, how we do work here. This was described by Thomas Kuhn in a 1962 book, which comes up on the next, The Structure of Scientific Revolutions. We're actually going through an identifiable phase called extraordinary research, where we're undergoing a paradigm shift. So again, these word slides I'll leave in, you can download a copy from FOSI and read through them. But you really are in a stage where we're trying to turn things around here, trying to go from this rather stagnant old model to something that's new and productive, both academically and from an exploration point of view. And again, a quote from the book by Thomas Kuhn, which you can read at your leisure if you download a copy. But basically, we are at a time now that's basically we should be doing some basics. I'm sure anybody who works at Petronas or another large oil company knows that big seismic programs are being finished off. They're not being started. Drilling campaigns are being delayed. This is a perfect time to go and hit hard these basics. So when budgets, they will get freed up. We will start exploring again. We've got the new framework ready. So it's quite a crucial time to be doing this. Okay, I'll go into some examples now because it's far more interesting and something you can relate to. But this episodic stratigraphy, this comes from the Ashnavid's book. I like it. It's a process. It's not an episode isn't a thing. It's basically defining the fact that it's episodic. This is the situation of Southeast Asia, schematically shown now. I've color-coded the unconformities and a bit garbled. Because a lot of people don't have full access to data. I'm lucky I've been around long enough, so I've sat in data rooms, I've made notes, I've read the original reports, I've gone through field reports, but a lot of people don't have that luxury, and they get this confusing picture of what's going on. Even what you're calling SynRIF depends a little bit on who's doing it and where by a small area. So we've got a very loose model that we really can't do much with. What I think we're at now for most of the area, and we're trying to publish now, is something that really balances. All these unconformities are now correlated. We see the phasage changes across them. They're related to tectonic events. We've got much better pattern, and from that pattern, new plays and new tectonic models will come out. So we're right at this cusp now, going from this poor, localized mishmash of data from 20 years of people doing local papers on their block and their block only, to a more regional view. And as I say, this applies to Sarawak, Sabah, Palawan, Makassar Straits, Java, Sumatra, North Sumatra, and Sulawesi. It gets more complex there. So again, this is going to be quite a major change, and I think it's certainly by no means finished. I think it's a crude first pass framework, and we need to develop this more to get plays out of it. A little bit on the speed of change. I've had discussion, particularly across Morley, about how quickly things happen. In Southeast Asia, things do happen very quickly. I'm going to publish some work on these examples from Northeast Java and Sarawak. The initial phase of sedimentation in Southeast Asia was under extensional stresses. So you get what they call breakup unconformities, which happen really at crustal failure. So there's no surprise they're quick events, major contrast. The examples from Mulu I showed earlier on showed that major breakup unconformity. The next slide will show us some of the history, but within the early Miocene, this has all changed and we started getting compression. And you think, well, compression by definition is going to be long and slow, and it is. But even within the compressional phase, there are 2 or 3 major reconfigurations that seem to produce correlatable events. And they are very quick. So I'm shocked how, and I think Robert Hall would agree with me on this, he's done some study on this, how quickly things can be uplifted and eroded in the tropics. So again, we need a bit more work publishing these examples. Certainly Northeast Java can be done. Onshore Sarawak is in press, just showing how quickly the Tinjar province, the onshore, is quickly uploaded and reworked as new piles of sediment. Very, very fast. So again, these aren't slow. There are slow ponderous events in the background, but these rapid interruptions of our main sequence boundaries. This is my current diagram. This is, it's in press somewhere. SEPM has got a volume coming out very shortly with 3 papers in. The Sarawak orogeny, I'm not going to go into much. That's basically the uplift of Western Sarawak. Kind of a larger area, but that's the focus of it. That happened all the way through the Eocene, terminating near the middle-late Eocene boundary. Even by then, you've got a little bit of extension on the far eastern side of Sundaland, rifting the Makassar Straits, rifting the South China Sea. They kind of started to decline on the Oligomycene boundary. This particular point will come time and time again. But in the west, around the Sarawak area here, we've got the Bungaran Trough opening. And that basically died off just as you're getting compression starting in the Sabah orogeny that grew. And things like the DRU, deep regional unconformity, that's a major pause within the uplift. People have assumed this is a discrete event in itself. No, you had uplift beforehand, it paused, lots of things changed, and it took off again. And the SRU as an acceleration of the Sabah orogeny. So again, we're getting these correlatable events. And what we're trying to do in the next year is publish a lot of data about why these are dated, because there's a lot of confusing stuff in literature about that and what happens at that time. But this is my summary of what I think is going across the region at the moment. Okay, an example from Indonesia. I showed this at CPEX last year, so if you've seen this before, if you were there, you'd have seen this, but it's still a very, very good example because I deliberately chose East Java and North Sumatra because both areas have got over 100 years of oil production. So you think we'd know them. North Sumatra, again, goes back to the first PSC wells, Telaga Said. This says a year 2000 diagram, and again, it's got the hat curve, almost by obligation here, down here, showing no real correlation to what was going on in the basin, at least that, and of course, this is misdated. But again, this is where stratigraphy has been for a while. We don't really know what's going on. We've got the hat curve, we've got observation, they're not reconciled. What do we do next? So I wrote up this thing on the North Sumatra area, published beginning of 2019. This is a very good diagram, but it's standard. It shows basically what I've got done schematically here, the rift. going to the post-rift sag with a limestone succession through here, and then you get the inversion of those mountains coming up. And this basic stratigraphic pattern was in all papers in the 1970s after Alan was discovered, until I did mine in 2017. And it even got into the classic book on petroleum systems, on the Bampo-Putu petroleum system. Again, huge amounts of hydrocarbon. I did, as a joke, work up how much this is worth in today's terms. It's a fantastic sum of money, but we don't really understand the area. It's really quite amazing. We can produce all this oil and gas and still not understand the geology. Because everybody went in expecting this. This is a standard modification of the steer's horns. We're getting rift, transgression over the flanks, reef growing as part of that transgression, then later on you're getting a regressive clastic fill coming in. This is a standard model for Southeast Asia. This is what goes on in North Sumatra, something very, very different. Major event here. Oh yes, so I previously mentioned this Bampo formation that got commingled with the Pirac. They're both black clay stones, but of course black clay stones are not really diagnostic of any environmental deposition. The classic area near Arran is a deep marine shale, very low TOC. The tight Bampo, I'll show you on a map on the next slide, is a long way away. It is quite different, but it's shallow marine with coaly beds in. But these two formations are different ages, but they've been commingled. No wonder we get confused. Also the sands. But really you had this tectonic event, and some more going on up here, grossly oversimplified. This is a map of that far northern area. There's the Arran field, fascinating story in itself. But this is a Pirac anticline. Now the IPA used to arrange field ships would drive in through here, stop through here, call it the Bampo formation. People used to take samples full of plankton, reasonably full of plankton. The black color comes from very fine pyrite. TOC, sort of by Azamira, less than 1%, almost always less than 1%. But this anticline was deeply buried. This was uplifted by the uplift of the mountains. You don't have to go deep in the Pirac A1 well to get into oil window. Yet this black claystone has got no oil shows in the well, no seeps, no sign of hydrocarbons. So this is not the source of the Arran. The tight Bampo formation is 25 kilometers to the south. And I can find no record of anybody been there since 1964, a chap called Morgan. I was talking to somebody last year about going there on a field trip because it's possible now. It'd be a very worthwhile thing to do, because these two got lumped together because they're black clays, and it confused the whole story. So again, this is a diagram from some papers done in the 1990s by Impex. I'm allowed to criticize these because I was involved with them. So partly my work, but again, you've got the obligatory hack curve down there. You think of the big Oligocene event. This is what I call pareidolia, seeing what you expect to see. Start looking at the writing. Fluvial channels, alluvial flans, lacustrine fill, bathyal, 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 bathyal. Now, something obviously goes on here. So, down here. And they noticed that was their P21 sequence boundary. They're still being guided by Eustace. Even though in the paper I persuaded them to highlight it's called a catastrophic subsidence. But this doesn't appear in the annotation for the text. It's not acknowledged in the sea level curve. It's almost an embarrassment of what this was doing here. This hadn't been, well, it had been published in the area. They thought they'd stumbled on something new, didn't know how to handle it. Not being unkind, they didn't quite sweep it under the carpet. They put it aside for another day and never got there to studying it. In fact, it had been seen before. This is work by Kirsting, 1974, Mobile. There's some very good field work just after they discovered Arran. And they'd seen all the outcrops of what they call the Agam formation. It's got a few limestones at the top, just barely gets marine flooded, but basically it's non-marine with coals in, immediately overlain, so it's not faulted. It's in many places an outcrop by fully bathyal Pirac claystone, black mud. They just call this Automeritic upper bathyal. About 600 feet is typically a guess of where it is. Across the border in West Thailand, SO drilled the West Line B1 well, and SO we use in Gulf of Mexico schemes to assign paleobathymetry, and they thought this is not faulted. It's seen in many wells, long, thick section of non-marine. One-step transition to what they reckon was 5,000 feet, 2,500, nearly 2,000 meters water depth, based on Gulf of Mexico analogs I could do about. It's bloody deep. So you've got this major step. This is a massive non-Waltherian contact. And this is the same thing they saw in the Banyulat Dalam well by Impex. They saw the same thing, halfway between these two locations. This covers a huge area. The stepped form of this, and I say Walther's law actually affects how you interpret unconformities. You can't have this massive, rapid shift in sedimentation in a well and then claim it to be slowly diaphanous across a basin. The two are related. There will be a maximum aggressive surface below this. There'll be a very, very condensed transgressive surface unit in here. So thin we didn't pick it up in the well samples, including sidewall cores in 2 or 3 wells that drill this by IMPEX. Very, very sudden transition. Same with the wells drilled up in West Thailand. And then it goes this deep marine section through here. So this is why they call it a catastrophic substance. It really was. And again, we recognize this feature of 50,000 square kilometers. So it's very large. Static events cover large areas, but this is an order of magnitude bigger. Nowhere do they have somewhere of 1-2 kilometers subsidence in next to no time. The only candidate eustatic change proposed for the mid-Oligocene was, of course, a sea level fall. This is a sea level rise. So clearly what's happening here is tectonic. So looking at that, we look back at the Allen field. I'm slipping behind schedule again. This was out of the Jordan and Abdullah paper, a very good paper, but again, they're putting it in eustatic curves. And I just wonder, are they hinting this is transgression, regression? This was a diagram done to show their strontium ages. They didn't give the actual numerical ages, they just shaded in, unfortunately. Mobil were one of the pioneers of the strontium method. So we've got some age control through here, but actually this has been published many times. What you don't realize here, I'll show you a geohistory plot again. There's not one catastrophic unconformity that Ricardo's seen, there's 3. Now I've drawn this in here with this degree of gradient. You could draw it with less, except I've been guided, as I show in the next slide, by the Banyulat Dalam geohistory that continues down. So you had the first catastrophic event here, well in excess of anything that UCC would have done. Again, we're not exactly sure on the age because the age control before is a little bit difficult, but it's about here. But then, of course, you had the event that lifted up this Bampo shale, eroded it, and then you had the Allen limestone growing on top. And of course, the Allen limestone had to then subside because it's now 3 kilometers. The Allen limestone was at sea level 15 million years ago from strontium ages, and it's now, Allen is on the coast, it's virtually at sea level. So that subsidence is undoubted. So again, we're getting these 3 major events, and there's simply nothing to do with the use of in this diagram. It's all tectonics. The key part here is that at Banyulat Dalam in green, you had sedimentation, non-marine, then it dropped down and it just continued to sag to its present location. There's the Allen, and this is based on one of the wells inverted in a graben in the eastern basin that was initiated at the second event. So again, if you want to read more on this, it's in my paper on North Sumatra, which is in marine and petroleum geology. But again, this is controlled by tectonism. Tectonism dwarfs Eustace. It controls the things that we want to look at, which is where the source rock is, where the structures were formed, where the seal is in place. And again, we've got basically these 3 periods, and these 3 periods are different in different places. So you can subdivide the basin. And this is something that's simply not covered by the deductive method. And you'll see this again with my Sarawak example. So you're getting these 3 different movements, and it's reconstructing these that's crucial that the eustatic models simply will not provide. So again, this is what's called the Kuhnian crisis. We're at this cusp where we have to throw away these oversimple deductive models and start looking at the data, building these for each area, then combining them for one overall model. One quick bottom line for North Sumatra is if you go to North Sumatra, and kudos to the people who are exploring that at the moment, because anybody who goes to files of the US Geological Survey, they're yet to find curves, just say nothing. Because what's happening there is it's got this huge number of wells drilled in the onshore area. Talaga side, at the guess, is down here somewhere. That was 1890 something. Somebody out there will know, I've forgotten. So 100 years of intense drilling onshore because it was cheap and easy. Some more drilling off in the shallow shelf. This area here has got very limited well control, some old wells here with very limited data. And yet both sets of data are compounded into one yet to find curve, which is wrong. It's just a misuse of statistics. You basically dilute, or you overprint your statistics with one set of data from an overexplored area. Where you really want to go is the area that's sourced Allen. Allen is sourced from something in this area. It hasn't come from the Bampo shell, which is down here. So again, this is a very simple method of saying, you know, if you're using yet to find as an area to guide you, they are so easy to abuse statistically. And this is a classic case in North Sumatra. Okay, an example from Sarawak. I've been going for an hour. That's longer than I thought. This is quite simple. It's straightforward. Again, this is based on old data in Laconia. And again, it shows us when you're looking at geohistory curves in pairs, you see a lot. This is that well in the west, the F19. It was drilled in 1972. Well done shell, 172 sidewall cores. This is actually a summary diagram by one of their competitors, another oil company just reviewing the area. And basically, they're not really seeing what's going on. They just see a lot of shale and a bit of limestone here. They're missing the point. If you actually color in the environment, and they did actually say possible disconformity or fault. No, this long, thick section of inoneritic, then big non-Waltherian contact. There's nothing on seismic here. I can't show you the seismic. And then it's continuously deep marine afterwards. So you're getting from the analysis a new picture. If you go to a geohistory plot, of course, it really brings it alive because that's the same well here. So you have this thick section, basically just getting to inoneritic. Then the bottom dropped out of the area on cycle 3 to cycle 4 boundary. Quite dramatically, and again, we know we have to create this accommodation space. It can't be any less than this. So it dropped down, continued to sag. Sedimentation, thanks to those sidewall cores and nanofossil work done 10 years later on those nanofossils, we know this is very condensed. Then actually at about cycle 4 to cycle 5 boundary, sediments started reaching the area, filling in that accommodation space, shallowing until you get the sandy section at the top. Then the 5 to 6 boundary, it drops down again to roughly its present position. So you plot this well that originally looked like a nothing well on geohistory, and you get awesome information out of it. Then you compare it to a well, I think it's 120 kilometers away. Oh, that's just downstream MMUs on the Mulu geohistory plot, where you had massive subsidence. Here it's less because you're coming away from this axis. So again, you've got this relationship with geography. I'll let you browse that at your leisure. That's the actual summary diagram showing basically how it's a very sharp contact. You have these little stringers of limestone. Then it shifts to just being more marly. It's planktonic rich, the calcimetry, the amount of, well, pelagic material in the sample, it becomes a marl. And it gradually fades up. Section, notice this casing here confusing the logs. But again, this is worthwhile looking at later on. Very condensed in terms of the ages. And again, the nanofossils were added later. They're not on this diagram. But again, very good well control for something that originally looked like a non-event, but it's got a lot of character to it. If you look at the well to the east, this well drops down the cycle 3 to cycle 4 boundaries, much more modest. It triggers this cycle 4 reef. We've got good age control from this. I won't deviate into that. I can do at length, but it's very well controlled until it gets to the 4 to 5 boundary, where this drops down. Now, Ed Koza did a paper in Marine Chungology in 2015. It's quite a good summary from this. I can test other aspects of that paper, but his seismic is good. And you see a lot of things happening at this time on his paper. So basically, that's the big event here. And again, you've created this accommodation space, and it gradually fills. A lot of sands. Then again, at the 5 to 6, it drops down again, slowly fills. So this is a well-constrained geohistory plot. But the fact is, in one area, this is a big event. In the next area, this is a big event. And we actually see tilting on seismic in this little gap before the reefs get unlapped. So while geohistory plots can be a little bit ambiguous, it depends what data you've got, and it should be documented. Comparing a few wells in one area will tell you such a lot that seismic alone will not show you. So this is quite an interesting example. Some of this will be published in this SEPM volume coming out soon. And again, the downstream MMU that was very large, that first diagram for Mulu, here is just a triggering. It's a modest transgression. It's a very weak subsidence. So very quickly, some of the cycles, I know people ask questions on it, so I'll quickly go over it. They're real genetic units. Now, what happened was, this second paragraph, they were developed in the 70s to early 80s. Shell was a little bit lax at publishing and documenting what they were. They started redoing that in the mid-80s. Just as the ODP work was really developing a whole new timescale. So it was a time of rapid change in timescales, and that confused the issue. The paper I did with Maslan in 2017 goes through this, and that unnecessarily confused the issue, and we've sorted that out, I believe. But that's why people stopped using the cycles. They just didn't quite know how to consistently pick them because they had different ages because of different timescales. Again, that's documented, and I'll try and skip over that to speed up. But they are real events. This is my latest draft of how I see the cycles, the latest ages I assign to them. And again, some of this is impressed. Certainly there's big unconformity here, a little bit more on these events. But these are real genetic units that turned on the limestone, modified the limestone quite strongly, and eventually, I think, terminated most of the limestones and also the Subis limestone. So a lot goes on in Sarawak that's been underappreciated. And it's people like Maz and myself have been trying to get geology back on the table for these seismic interpretation. A lot of interesting stuff in Sarawak. Okay, move on to East Java. Hopefully you can still see the coast of Java on here, coming through here. Surabaya, Madura Island is that weak line through there. I put this map up because I want to talk about the Sibu Graben. This was in my paper again from 2019 on East Java, but it's a good example. Excuse me. The NSA-1D is a great well in this Sibu Trough. It used to be called a Graben. That's not a fair description. This is my latest. In fact, it's not quite my latest stratigraphy for East Java. This is a nice color version. The horrible term nimbang, which everybody knows I hate, but it's sort of stuck with it. But even these terms are very ambiguous. A lot happens. I'm just going to focus on this event and then a few overall comments. Again, in the mid-Oligocene. So people talk about the big hack event in the mid-Oligocene. We do see something, but not what the eustatic model suggests. This is from the paper. Basically, NSA-1D showed its initial transgression, reefal limestone, low relief. JS53 actually produced a reef with some oil in. Big drowning event here. This is the Eocene-Oligocene boundary. Look at that gamma drop. You'll wonder why I'm pointing this out, but it'll come up on the slide in a few minutes' time. This is quite condensed, picks up. Then at this time here, within NP24, they lost circulation, set casing, and then got samples again. They've got sidewall cores through here. So between two sidewall cores, getting this contrast, we know it's NP24 where the reef started. So all this stuff is very deep marine. These are all classic bathyal markers. And these are all reefal material. So it's a major change. This is basically when this horse got pushed up and another horse on this side called Horseshoe Reef, isolating a low in between, which is the Sibu Trough. That's a massively important change because people thought this was just another graben in East Java that was produced sometime during the Eocene as a guess. Well, it wasn't. It's produced in the Middle Oligocene by isolation of these two elongate highs. So there is no syn rift in here. So there are oil shows nearby, but that's a separate issue. So this is quite interesting. It shows how this mega sequence, this tectonic stratigraphy approach, shows you quite a different history because basically, as far as I know, nobody's ever drilled a deliberate subreef play. Reefs are not going on basement. In parts of East Java, they go on uplifted sections, some of which are quite large, containing entire petroleum systems capped by a seal. It gets truncated a bit. But of course, seismic gets quite poor down here. And you've got to believe that reefs don't go on basement. You've got to believe there's a section to interpret your seismic. So there's a new play type that's coming out of this model. Now, I've discussed this for years, and I'm sure people have started looking. I've seen seismic to the south that shows features below here. Then I discovered in the late 1990s, before BP pulled out, they started to see this. But then as a corporate decision, they pulled out of Indonesia. So they had already seen section below these limestones. So that's a play that's revealed by this new approach. I cut out a few slides here on the Kawengan Moody Banyu Europe area. It's worth looking at this area because, again, onshore, Kawengan Field has produced about 120 million barrels since 1920 to the turn of the century. It's in decline, not very much in decline now. Banyu Europe, a great story on that. I was working in this area, drilling Moody with Petroma Trend. We badly wanted to get in here. That's a separate issue, but it's a great looking reef. But even then, because basically Banyu, we saw it here, there's a bit of sand above it, it's quite shallow. The grabens around the side are quite deep. So basic 1D basin modeling will tell you that you need 500 meters of top seal to get capillary seal over the reef. So the reefs weren't effectively sealed until the Pliocene. Meanwhile, these grabens, this syn rift in the graben, was at 4 or 5 kilometers. It was already in the gas window. So when we tried to get Banyu Europe, we expected it to be a gas field. So when they found the big oil there, it was quite a surprise. This I published as a favorite section on the Rembang well, and this explains why this is the oil source for Banyu Europe. It's a lot shallower than the original syn rift. It matured later, of course, because it is shallower, and that has been typed geochemically to the oil at Banyu Europe. And this is quite important because this diagram, which is based on seismic, just simplified, and it's in my book on Java, you see this deep marine section, differentially uplifted, a reef at Perwa Daddy, this classics over here. This is a very important time. Yet all this is included in this horrible term nimbang. Some people put top nimbang here at the expected mid-Oligocene seal fall. Some people put top nimbang here, some people put top nimbang here. So it's inconsistent in what it is. But you've got 5 or 6 different units within here with massive facies contrast. That's why it's such a useless formation term. So you've got to really build these models up using observations. You can't assume syn-rift, sag. You've got to look at the data and build something more complex. And I say, I don't know of anybody who's actually tried to map this regionally, which is quite surprising because obviously onshore is very difficult with the seismic, but we're not really chasing these things as aggressively as we should. That's the message. What we've ended up as, basically, this is from a paper 2006. I've since found it in more. This is from a very large multinational oil company that shall remain nameless, but you can probably all guess who it is. They were forcing it. I knew the guys working in Jakarta. They didn't really believe in this, but for head office, they had to force it into the TB scheme and all this nomenclature. And basically, it's forcing something that doesn't fit. We know if you drill in East Java, you get either Kudron or limestone at this time, or you get Batu Raja, or in the deep marine setting, you get the Pupu. In fact, on this well, you can actually see it's behind my little, let me move my guide here. This is a Kudron Unit 1, the reefal part. And in this well far to the southeast, this is the condensed Kudron chalk. So we know this basically is classic starvation, but it's not shown on this diagram because they have to force their data to fit an inappropriate model. So while this looks very technical, it really doesn't help. Now, this event here, I mentioned that gamma drop on the previous NSA 1D. That's this event here. This is a huge event around the region. And yes, they've got non-conformity here, as they have here, as they have here. You know, there's lots to choose from. Andrew Meal has already written a paper on this sort of, what was this wonderful title, An Event for Every Occasion. So yes, they've got an event here, big deal. This is a biggie. What happens is, this is an essential deep. This is JS14, because it gets inverted. This, as I covered in my paper, this was triggered at this event. There were no basins here, and suddenly they were triggered, very rapidly going to limestones we can date it on here. By opening these basins, the central deep and the associated basins around them, they trapped sediment that was going to this location. So in the late Eocene of the Makassar Straits, you're getting thick sedimentation. And we have very good age control in deep marine settings here, but right on the Eocene boundary, there's that gamma log break and sediment starvation. So it really is very thin, and then that continues as condensed and ultimately getting the Pupu limestone at this time here, just down through here. So this is a major time of change in the region, and it's simply not, you don't see it on this diagram. So basically this model is very technical, but it's got no predictive power. You're fitting something to an idealized but inappropriate framework. The inductive model is predictive. You've got to document all these different steps, but eventually you produce something that will dictate what must be, as you see these faults on seismic, becomes a much better tool for science. And we've been neglecting this. And again, we just see, as I showed this before, the whole Kudron reef section just pops up in their diagram for no real reason and disappears for no real reason. And it doesn't really show what it is anyway. So again, this is fitting observations into an inappropriate model. You're not going to learn anything, and you certainly can't predict anything from it. Okay, the last example I've got here is something I'm doing now. And I've been looking at this for some time. Some of the students at UGP started working up here, but then they got misdirected. I think it's a great area to work in. Pointing at the screen, you can't see that. Proto-South China Sea. This is the most popular model. You'll all recognize this is one of Robert Hall's models for South China Sea. I am a big fan of what Robert Hall has done. He and his group for 15 years more. Tremendous work. But that doesn't mean you can't criticize it. And I have problems with this model. And this is the most popular model. Now, just a clarification here. I'm going to criticize something called a slab pull model. But slab pull as a mechanism is still a very valid method for driving plate motion. But this is just a slab pull model. The alternative is this Deponier model. You're all familiar with this, the extrusion model, collision of India. This explains these large dry slip faults. And his model was that basically this was just pushed down, leaving a gap behind. And that created South China Sea. The slab pull model, or the more precisely Proto-South China Sea subduction model, has this oceanic crust here subducting at this point here, creating a volcanic arc and pulling the dangerous grounds until they collided. So it's a different mechanism. There's rotation of Borneo and other things that come out of it, but this is by far the most popular model at the moment. I have problems with both of them, and we still haven't resolved this fully, but there's a lot of data that we need to consider on this. Because I'm very keen on dating things, I think a lot of things that happen in the slab pull model, the Proto-South China Sea subduction modeling, their dating is out of sync with what we know to happen in the South China Sea from magnetic stripes and what we expect, the age of the volcanism, the age of the overthrusting. It just doesn't work. But we're becoming used to this model since still in Wangin, and we're basically stuck in this rut with this model. I'm going to show you some examples from the Kudat Peninsula, which really challenges quite hard. But first, I'll just that's your own fun reading later on. The paper by Silva and Wangin is an IODP volume, so it's available online. I've got a list of references at the end of the presentation, so you can always find this one. That I'm not going to go through now, we're behind, you can read that later on, but it's very interesting looking at why people thought that this was a model. Wangin originally thought the reverse, and I think he's probably right. Okay, diagram. So this is basically topography and the Cagayan Ridge, the Sulu Ridge. This is a compilation of the radiometric data from, in green, the Cagayan Ridge, where it continues up to the Antique Range of Panay Island. This is North Palawan, which is continental. We know it's continental because up here on these islands, we've got Permian limestone, Permian at one of these limestone, and of course we've got a lot more Mesozoic outcrops in these areas. Southern Palawan, North Borneo. So people thought subduction over here, then you'd have this island arc, then a back arc basin. They forgot about this. If you look at the timing of these, hopefully this will come up, age of spreading in the South China Sea, the Barkhausen model has been about 24 million years to 20 million years. I favor that model, but I could be wrong because people like Ambrier say it starts about the same time, but continues to about 17 million years. This hasn't been completely resolved, but that's when the South China Sea actually moved and it stopped. The drift stopped. Before then, of course, there was rifting and thinning, but this was the actual rifting, the drifting we can measure on magnetic stripes. But look at the age of the Cagayan arc and the Sulu arc. It's very active, even after all this motion is finished. So that's the peak activity of the Cagayan arc. The Sabah orogeny, the big overthrusting of Palawan and the Western Cordillera, pretty well dated from about 17. It builds gradually, 18, 17 million years. By 50 million years, definitely happening. And it continues through to about the Tegopi Unconformity, about 3.5 million years. So that big overthrusting has nothing to do with movement in the South China Sea. It clearly postdates anything. That's the age, and that's poorly dated, this spreading through here. The magnetic stripes are very hard to read through here, 2 attempts to do it. But we know from where it's intersected by these ODP cores, we know the age of it. And basically that's the middle here too, and that doesn't really fit being a back arc basin, it should be a lot older. What happened was, Robert Hall, and I agree on this at least, he's got subduction coming from this southeastern area. So originally, the Cagayan Ridge and the Sulu Ridge were one ridge together, and there was inter-arc spreading. This is seen south of Japan more recently, but the arc split. The more distal arc then fades and dies, and the ridge, the arc nearest subduction continues. And when we see this in these ages, Cagayan dies, Sulu continues. That supports the idea of getting rolled back, pulling this apart. So this is a back arc, so subduction this way. So, yes, the last key point up here. We know we've got Permian right up through here. There's Triassic and I think Jurassic up in this little Bungarangan Peninsula up through here. There's even one date, but there's no room for a collision zone. If you get the Proto-South China Sea subducting, there will be some sort of accretionary wedge, 4-arc basin. As it collides, this will go up into being an orogeny, and it ain't there. In fact, one of these igneous ages is on the wrong side of the suture. That's hard to explain. So we don't see any sort of collision zone between the North Palawan and the island arc. It's missing. I'll miss those wells because I can't show them. This is the magnification of the Panay Island, the Burangan Peninsula, showing very sharp contact. Yes, there is thrusting there now. I've been discussing this with Chris Morley, who's a very good guy to discuss, very knowledgeable on this stuff. But when I found ages on this thrusting, it post-dates again any of the igneous activity. It's not due to collision along this area. This is the North Sulawesi showing the invocation accretionary zone marked with dashes off Halmahera. That has to get crunched and fit in this tiny sliver, and there simply isn't the space to do it. So I've got geometrical problems with this. The most recent data I've been looking at, I think, is the clinchers from the Kudat Peninsula up here in North Borneo. Now, if you look around here, you'll see basically it's surrounded by oceanic crust. In fact, the predecessor chance is the other side of a postulated subduction zone. So the Kudat Peninsula really is an anomaly when you see the outcrops there. But it's been misdated. This is why you've got to get stuff dated correctly. These are papers by the University of London group. And again, generally, I think what they've done over the years has been very, very valuable, but that doesn't mean they're perfect. They've assigned an age to the Kudat Formation here of early to middle Miocene. There is no data supporting this. I've actually spoken to Van Hattem and some of the other people there, and they're citing the old reports. They haven't got all the old reports, but they're basically using larger pelagic foraminifera to determine an early Miocene age. This is not true. Bit of history. Back in the 1950s and 60s, when they were doing this work, they had different definitions for what was then lower Miocene and upper Miocene. They actually observed the fossils for the latter stages, TE1 to 4. So again, this is from Wilson mapping to the south. This is actually from Stevens in the Kudat Peninsula. Lower Miocene, Aquitanian, Tertiary 1 to 4. These are the fossils. Upper Miocene, TE5 and younger. Well, we now know from very good work, this is stuff that Ham Van Gorsel, Bob Morley, and myself published a few years ago. We didn't do all this work. We represent 30 years of Robertson Research and other companies. We're compiling all this stuff for publication by Bodita Sedimentology, but this is basically just repeating what's been established with the Earth and Wells. TE4 to TE5 is close to Globogenoides datum, the Kugelei datum, top of MP25, basically at the Oligocene-Miocene boundary. These, by the way, are proxies. The Oligocene-Miocene boundary is now defined as the top of the Chattian, which we don't see in Southeast Asia. We do see the Globogenoides data in Southeast Asia. They have been used as proxies. But this is where that TE4 to TE5 boundary, this is what they used to call lower Oligocene, this is what they used to call upper Oligocene. So this is simply a historical problem. And this is corroborating data from Tony Allen at CSIRO using strontium dates to the same thing. So again, this is just resetting the ages, doing some homework, and you find a Kudat is in fact late Oligocene. I hope to get it finished in time for today, but I have a map of all the surveys done in this area. There's one done by Reinhardt and Wenck, 1951, a super survey, and we can use their work right through to the more recent work done in a few years ago, plotting all the samples, and there's no doubt there are some Eocene locations in here. I'm not going to go into the fact that they're reworked or not. They're in clay, so I doubt they're reworked. But certainly they're Oligocene, mostly late Oligocene in age. So again, what was the source of this sand? Very, very sandy. These are measurements from Felix Tonklou, done some very good work in the area. Paleocurrents for the Kudat Formation coming from the north. Now, this doesn't surprise us because Robert Hall's group, Van Hattem and Simon Stuggart, studied the garnets and heavy minerals in these, and they're totally unlike anything in the Crocker or anywhere else on Sabah, anywhere else on Borneo. They've got common garnets. You only find very rare garnets in the Crocker sands, and things like kyanite, which aren't seen at all in the Crocker. So not only is it paleocurrents things coming from somewhere else, but the heavy minerals are seeing that too, and the paleocurrents from the north. Well, there is nothing to the north. This is a quartz-rich sand. This is a map I was hoping to replace, but these are basically some of the samples that are definitely TE1 to 4 late Oligocene. Also on this area here too. So basically intensely deformed during the late Oligocene, because we know offshore, and again this was published in a paper a few years ago, we have what they call stage 3, very weakly deformed at Tigapapa and Atumandi, that post-date this deformation, and these are well dated. So again, age is quite crucial to sorting out a history. It sounds obvious when you say it, but if it's done sloppily, you get a bad history. So this I'll publish soon because it's really quite a useful compilation. But the question is, where did this sand come from? It's rich in quartz. It's first cycle sand. It's about 60% quartz. There are plagioclase and a few lithics, including 5% chert. But on the old model down in the bottom, there's nowhere in the slab pull model, the proto-South-China subduction model, that could source quartz sands, let alone garnets and kyanites. If you adopt my model, that basically you don't have any subduction for a proto-South China Sea, you have basically a little bit of southward movement of Palawan. We know from dredge samples that the German group, Kudras et al., took dredge samples on fault scarps through this area, and they found some lovely metamorphic rocks rich in garnet mica schists and amphibolites in this area. In fact, I think there's a couple more up to the north. I haven't plotted those yet. And also some Paleocene and Eocene lethal limestone sources to source into this area as we were working. So that fits nicely. You've got a source for quartz sand from a continental plate and the garnets, whereas here there's no source for quartz sand or for garnets or for kyanite. So again, I think when you compile all the data, this really blows the proto-South China Sea subduction model or puts severe pressure on it. There are other reasons too, but this is quite a nice crystallization of the arguments. It really doesn't fit with the model we're all so familiar with. So again, I've spoken long enough. Oh yes, a little bit more down to the southeast, work done in Sabadanhe Gomantong limestone. Laura McGonigal did some work through here. I helped on it a little bit, where they're seeing basically the limestone, clean limestone. I start at the bottom. The Labang Formation is a bathyal fleece. During the mid-Oligocene, it's starting to get transported debris flows of limestone. Something is triggering slumps, calciturbidites coming in, and we've dated those. Then it continues the deformation to create an uplift and angular unconformity, and you're getting a lot of uplift. That previous imagery showed that strong northeast-southwest, northwest-southeast lineation. That terminated, and then the Gomantong limestone grew on top of this uplifted fleece. So that's this major unconformity between TE4 and TE5. And going back to Reinhardt and Wenck in 1951, this is what they said. This was the biggest event to affect northern Borneo, and I'd agree with it now. So again, a lot of these important conditions for history are being forgotten about. And really analytical work and a new look at the seismic brings a whole new meaning to what's going on for the geology here. So Kudat summary, the fact we've got a continental source for the quartz sands and the garnets, which you don't find in the South Divide Crocker Formation, basically I think this is a severe challenge to the model that all of us will probably sketch and put. When we're doing a presentation to management or investors, you basically show the Robert Hall model as an introduction and you zoom into your area. I'd say we have to go back and revisit that. There are implications for plays coming from that. There's strong deformation during the later Oligocene, and that was terminated by the onset of seafloor spreading facing Sabah. So again, a very different model coming out. However, having knocked the Proto-South China Sea subduction model, this isn't compatible with the competing Teponier extrusion model, which is purely extensional. It can't explain this local intense compression. So again, a new model is required. Both of these are found wanting. So I'll be writing it up soon. Not quite ready to share it. If you are interested, get in touch. It's just scattered on various files on my computer. I've also got a lot of work on North Borneo coming out. But basically, we're coming towards a paradigm shift, which we require a lot of documentation for, where we're going to start relooking. In fact, let me get to the conclusion slide. Southeast Asia is not mature for exploration. Definitely not. It's been stuck in it for a long time. And we don't really understand its basic geology, the plate tectonics, what the basins are, what the provinces are, because we've stayed with these same old ideas for 30 years, because we've been doing deductive methods that restricted our thinking. We spend less and less on analysis. Anybody who's tuned in from Core Labs or CGG or any bicep, they know that budgets for analysis are down. We think we can live without them. We can do it all on seismic. We can't. We need both because this is a complex area. So we've been stuck in the same rut. We need to turn out of that. We will get better geological ideas, better ways to interpret seismic, genetic sequences, not false sequences. I believe there'll be new discoveries. In fact, that's the next slide. This famous quote here by Park Dickey is very, very appropriate. We lack new ideas. We lack new ideas that are documented and tested. And I think we're nearly at that stage now, because we can't say, hey, I've got an idea. If you're asking for several $1 million, you've got to back it up with something. I think we're getting to that point now. We can actually generate new ideas that are valuable and we can back up. So my predictions, I think we are really going to see a major paradigm shift in how we look at the geology of Southeast Asia in the next 5 years. We're really close to it now. I'm talking to people. I believe this figure here is from a paper by Sabin Zadovic. It's still got Proto-South China Sea on here, and we need to discuss this because they're modeling what they think is going on with the plates. We need to revise this model, convince them that we're right. And these models basically model the mantle in 3 dimensions, because we know from work in Australia and elsewhere, as plate subduction goes on, it can create what they call epirogenic movements. The entire crust responds. I'm waving my hand here. It can cause wholesale uplift and subsidence, creating modifying basin, sea level changes, transgression, regression. We've never really tried to bring this level of complexity into the plate models of Southeast Asia. We've been looking too much flat files, sometimes on curved surfaces, but flat plates moving, bumping into each other. I think we really need to start looking deeper at what happens in the mantle, because there are effects there on modeling that could explain a lot of features we see, like Borneo, southern Borneo, that uplift I showed quite early on where the sediment source rotates. What drove the uplift of southern Borneo at about 25 to 20 million years? We have no idea. I think the answer will come from something like this. It isn't plates moving, not laterally, not far. So I think basically we'll have new models in a few years' time that really will supplant what we've been used to for a long time. I think there will be a new generation of plays. I've already seen some. I'd like to see some more seismic. I'd like to get companies interested. Because we know in other regions like the North Sea, they get this sort of new looks every 10 to 15 years. The Johan Sverdrup field drilled by Lundin, I just left Lundin to join Mitra Energy, and they drilled this feature in the North Sea, and they asked me for examples relative to this, but fascinating story. 4th generation field in the North Sea, and I think it went on production last year, and it's now something like 600 million barrels recoverable. So that had been overlooked for 20, 30 years in the North Sea, and it required a new way of thinking. That is not unique. We've compiled a list of other things. Ian Long has done the same. Big discoveries in mature areas. They require a new way of looking at your data. So again, I think we'll start coming out with these ideas. I think we'll hopefully get some investors attracted to the region. Hopefully the NOCs will start drilling some of these and making discoveries, because Asia will need these fuels. And I think basically we'll see a major turnover. Some companies won't adapt and go looking for these and will pull out. And I think there'll be a major change in what we see in academia too. So I think that just about wraps it up. I've got a last slide here about STRATOS. As I say, myself and Peter Woodruff are looking to try and help assist this new generation of exploration. We think it's fascinating. And we want to pass this on to the next generation. They've had 20 years of learning Workstation, the Workstation software changes, and they've neglected their geology. We'd really like to convince people that it's worth taking a look at the basic geology again and building a whole new geological model for the region. And that's about it. An hour and a half in. Let me take a drink and I'll answer any questions anybody has.
Okay, thank you, Peter.
Yeah, maybe we have Mas Ricky.
Yeah. We will move to the question session, yeah? Okay, thank you, Peter, for your very interesting presentation. You mentioned about the importance of the inductive thinking, yeah, especially in Southeast Asia, because we have a very different tectonic that will affect the stratigraphy. Yeah. We have some people want to have a question to you, and the first one is from David Gold. David Gold, you can turn on your audio, please, to ask Peter directly. Mr. David Gold.
He's on UK time. He's probably got some coffee break.
Yeah, okay.
My computer froze. Hello, Peter. Very nice talk.
You can join us.
Yes, I did. Yes, and selamat sore to everybody in Jakarta, and selamat siang from the UK.
Yeah.
Just a comment and perhaps one question. I've sent you quite a few questions, but perhaps we can pick these up at another time. But yes, just a general comment. I completely agree with what you've said there. I mean, the use of global eustatic sequences in Southeast Asia just doesn't work. And we have to remember that these sort of global sea level curves were created for the Arabian plate, which is a broad gently inclined ramp and has been for 200 million years or so, and Southeast Asia just isn't that at all. So it's much better to use an appropriate localized scheme, whether it's Bob Morley's VIM schemes or some localized relative sea level curves. You just have to use whichever one's most appropriate for your data. I guess the question that I have is that, have you tried incorporating any of your observations or any of this work with stratigraphic forward modeling? You mentioned COSA. I think COSA has done some forward modeling on the Sarawak carbonate buildups. I find that these forward models are really useful to identify the different controls on the deposition of some of these sequences. And more often than not, sea level, these sequences can form totally independently of sea level. And we can form all these carbonate buildups or stratal geometries based on variations in sediment supply or subsidence history. It might be just quite nice to try some of this stuff on some of the observations that you have.
I haven't done it myself. A guy called Syed Harun at UTP has just done his doctorate on modeling in the GIN10 mega platform area. That was very good work. So in some areas it is being done. My hands are pretty much full sorting out the clutter of data from people working little postage stamp areas and getting those documented clearly, what the age really is as far as I can tell, error bars, you know, how accurate they are. So my task is just sorting out this, because I've had the luxury of being here for so long, I've seen the data and I can get permission. Petronas has been very kind and given me permission last year for some work. Getting this out, getting the housekeeping sorted out. And it's really the next generation, like I said, who will do the next set of work, like the forward modeling. The framework, though, I think I'm happy with the overall framework. There's a few holes in it, like the west coast of Sumatra. Maybe then you can start looking at these techniques, but we need to just base it. In fact, we need labs like CGG Robertson's to make an appearance in Southeast Asia to help with the analysis, because there's so many wells and outcrops that were drilled, and for that well, certain aspect wasn't a priority. They didn't analyze for fission track or for strontium or for whatever. But we need to go back in and get those samples out. There's a big slug of work that needs doing in the next couple of years to, if we want to get new investors or even the NOC spending millions of dollars drilling wells here, we have to back it up with some work. And that will include a lot of basic confirmatory and even exploratory laboratory work. So that's my priority at the moment. But yes, I agree, forward modeling. The computer software is getting very sophisticated. Sabin showed me some of his 3D Earth models recently, and they're really impressive. But he's having to rely on old papers for ages of when things happened, and I need to correct that first. So agree, the forward modeling is an important technique, but I am still in housekeeping phase, sorting out some of the errors of the past or the misinterpretations of the past.
Yeah, I've been talking to Sabine, and we've been trying to find something, or find some time that we can work together on some forward modeling and using some of his mantle models. And I think he has some forward modeling software as well that he uses, or his group uses, called Badlands and various other bits of software like that.
Yeah, but the software is there. It's very impressive, but you know, you've got to get good inputs to it, and error bars and those inputs too. I mean, we know certain things did uplift, we know certain things went down when. So we need to get that data set so we can test their ideas. Do you see substance this time? No. Why not? So it's getting that basic framework sorted out. The data's there. It's in the files of the Geological Survey in Bandung, of the Geological Survey in Malaysia, the old well reports and region reports. It's just a question of doing that. That's a priority job at the moment, which I think we're, say, 85% of the way through. Then getting it out peer review, getting people like Chris Morley to look at it hard and find the faults in it. Once we've got that true peer review from experts like Chris, then we can go to people like Sub and say, no, we really believe this data set. It's not what you have at the moment. Now model this and see what happens. That's, I think, will be the next step. So we're in that transition phase. We need to finish off the revision. We need to get some of those old wells and field outcrops analyzed. And then I think really start ramping up the forward modeling side.
Yeah, I've been having lots of fun with Pete Burgess creating models for the Middle East and presenting these at conferences, saying that all these sequences aren't sea level controlled, and you can create autocyclicity within carbonates just based on carbonate production rates.
Yeah, but, I haven't seen the final version of Syed's thesis, but I know early on I was checking him. He's seeing basically the reef was tilting. He could see these effects, and a lot more happening in the reef that he could accommodate with a tectonic theory. And again, it's having the hard data. You know, if you assume the Hack curve, you end up with a descriptive process. It doesn't, like that diagram I showed from Exxon for each job, it doesn't really do anything. It accommodates observation, but it's not very predictive. Hopefully by getting our house in order with geology, the stratigraphy, we can make it a predictive science, saying, yes, your model fits this and only this, therefore it's reliable as a forward model. So I think it's an exciting time, but there's a lot of grunt work still to be done. But I think both for academic geology, plate models and so on, lots of interesting stuff. But I really firmly believe, I know there are new plays to be found in Southeast Asia. What we need to do is get the oil companies coming in. I hear Indonesia is adopting some Egyptian model for exploration to try and entice investors to come in. If the technical community at FOSI can sort of try and push a new technical model and say, now we've got new technical ideas, new plays, or even old plays with greatly changed risks, I think we can get people coming in and spending money looking at this. So what I'm trying to do is, this is why I'm making a copy of this presentation available. I want people to come back to me with ideas, to criticize it, to find faults in it. There will be. But we need to go through this sort of transition period to a new evidence-based model and not be driven by imported models.
I have several other questions, but I think I'll pass over to
No, that's
Bintang.
okay. That's okay. You can ask, sir. That's okay.
No. I'll pass over to Bintang and other people.
Okay.
I'm sure.
Okay. Thank you, David, for your question. Have a nice day in UK.
Thank you very much.
Okay. The next question from Bintang. You can turn on your audio, please. Yeah, Bintang. Okay. What's the question? Let me just read it. Okay, Peter, it was an insightful presentation, and it drives me my interest to ask about the North Sumatra Basin, which is clearly shown that in the western part of this basin have a very limited well data. Is it because there is a less exploration research without using this method as you described here?
Yeah, basically the history of Aceh is a little bit unique because obviously they found the Aran field. Mobile as it was then went fully into production mode. They'd been doing some very good field work until then, but then they had this, they weren't expecting a reef at Aran. There was not in their well prognosis. It doesn't look like a reef on seismic, but they found it. It was big. It was bigger than they thought. So they deflected from exploration to evaluate and produce. And they never really went back to exploration. Then, of course, there was local politics involved and fieldwork became quite difficult in the area for some time.
Yeah.
So you have this generation of work from the 1970s, which is largely available now. It's been passed around people. Good field reports. In fact, the 1920s, Han van Goorsel mentioned a guy called Zwier Zicki in his talk 2 weeks ago. This guy mapped up in North Sumatra in the 1920s. I've been through his work. It's superb work. The trouble is finding out exactly which location he went to get the old maps out, but excellent work. We badly need new field work up there. Some of the old wells done in the 70s, if they still have samples in storage, I'm not sure we can use them because samples do decay in storage. But some interesting sections, badly needs new field work. But most of the work was done to the south. People quickly drilling wells on little prospects, creaming curve exploration in the little anticlines, offshore in the shallow water. So for various reasons, there's a lack of exploration in the deep water section. The JAU Jambu Utara wells found a low stand fan with some gas in it. That was great. Difficult to commercialize out there, but that indicates something is going on. The new seismic is very good. But we lack the geological models to interpret that seismic, like where the source rock is. And actually, as you sneak around the coast of North Sumatra, there's a well called Raya 1, drilled on the opposite coast, on the north side. I've only seen old reports on it. I'd love to see the original work and get more stuff around there. That does not fit anything in the region. So get that out, analyze it. We've got this preconceived idea of the North Sumatra Basin, which we just split into two. But we've got no ideas where the boundaries basin was in the Oligocene. Some of the wells in North Sumatra, they hit sands at TD. I'm not going to mention names with operators on. They thought it was the Parapat Formation, because everybody knows the Parapat Formation is deep. The Parapat is a shallow marine, non-marine sand. This was the low stem fan turbidite. There's all sorts of clutter up there I need to sort out. We need to ask questions again. So yes, some of the old wells, if we can get them out and analyze them, there's something that can be done. But I think North Sumatra badly needs some more field work. Access, I've looked at it, is a little bit difficult, but the old maps are very good. If anybody wants georeference maps from the 1920s and 30s, I've done it. I can recommend places to go to. There's oil seeps. It's a fascinating area, and we're not sure where the North Sumatra Basin begins and ends. A lot of history is unknown to us. We take simple assumptions. I can't see any big new plays coming in this area apart from the things that are being explored at the moment. But then again, I don't know because I know so little about it. The thing is, it's so cheap to do this kind of work, field work and analysis, compared to shooting seismic or gravity or this other stuff. But we're just not organized and incentivized to do it. And North Sumatra, like so many areas, is crying out for some basic field work. And yet oil companies are very loath to do it. They've got to really do it before they sign the block, unfortunately. You've got to do field work, then sign blocks, then go exploring, so it gets a bit out of sync. But there's so much you can learn for North Sumatra or for the wider Tarak and Mangley Hat area, just by some basic field work that's been overlooked. So North Sumatra I'm quite excited about. I'm looking forward to the next round of well results. I've seen some of the seismic, but I'd like to see that well result integrated with the seismic. But it's an excellent new ventures area, a very exciting area.
Yeah, thank you. Yeah, I agree with you. This very exciting area. I think there are many companies start looking North Sumatra now. Currently, yeah. We can move to the next question from Soekarno. Yeah, Pak Soekarno, you can turn on your audio. Yeah, he's a stratigrapher from Core Lab.
Yes, I know Soekarno well. Yes.
Yeah, Pak Soekarno.
Hi, yeah. Steve. Yeah. Peter, how are you?
Hi, I'm fine, thank you. How are you?
Yes, great presentation, is it? Yeah, I want to ask something, a small scale of topic here, because I know I want to ask about the forums, because I know very well your first love is in foraminiferous, Peter.
Well, actually, it's in mineralogy. I sort of did forams just to get into geology, but yeah, I have done a lot on the forams. They are fun. They're an interesting group, often, as you well know. Yes, yeah. Go ahead.
Okay, yeah. If we look at the cycle in the Sarawak cycle, mainly in offshore cycle, there is one cycle in late Eocene to 8 cycle 8 in Pleistocene. Yeah, I am currently working on the wells from Sarawak, and how to assign it the transition of every cycle. For example, from cycle 4 to cycle 5, based on forum assemblages from the shallow into the deep water. That's all.
Well, basically, well, the original definition of the cycles, they went out there looking, they've been exploring in the Serai field, Miri field, offshore Brunei and North Sarawak, where they could correlate on the floods, marine floods. So they went out into the offshore area expecting more of the same, correlate on floods. That's why they used the term cycles. They were expecting that. They soon found out it was far more, but they still define their cycles on these floods. So the 3 to 4 flood, yeah, thanks. So that's the 3 to 4 flood. Now the trouble is, somewhere, and I'm not sure where, the 3 to 4 definition got garbled and got confused, but that's the original definition. So that's a flood. Now, where you get the Laconia limestone, you see that flood as a limestone appearing. In the Belingian area, it's a sod to do. Sorry, it really is tough to correlate it. I know the 4 to 5 is a little bit easier in Belingian, but 3 to 4 in Belingian is really hard to pick out because the flood's so weak. So again, unfortunately, that's just the way it is, particularly on some of the old wells with wide spacing of samples. But it is a flooding event. What I've done in a recent paper for the SEPM, looking mainly at the carbonates, I've actually divided cycle 2 and cycle 5 in half based on regressions rather than floods, because they're big uplift events. but all the original definitions were based on transgressive surfaces, which under the Embry would be basically have a maximum regression surface and a transgression over the top. Shell would be using the transgression, Embry would be using the maximum regressive surface as a boundary, minor difference. But yes, I agree with you, it is difficult in some areas, particularly Berlingian areas in the south, where you're getting less and less marine influence. So sorry, it is just difficult there. A lot of these wells were just done on widely spaced samples for biostrat. If you can go back and get the original samples, don't just look at the process residue, so they pick slides, look at the process residue for any floods of glauconite or anything like that. I like looking at process residues because you can do it quite quickly. You just scan through, looking for these shifts in character. Once you start getting picked slides, you're obviously losing a lot of that background information on glauconite or something else that somebody looking at the wall slide would see. That's the best recommendation I can make. But you see, now with good 3D, you pick it in one well, you can extrapolate it to other areas. But again, I've worked in the Berlingian area. That's really tough to pick it in there. It is.
Yeah, thank you. Okay.
Any other questions for Sukarno? Just get in touch, yeah?
Yeah. Thank you, Pak Sukarno, for the question.
Yeah, thank you.
Yeah.
Welcome.
Yeah, the next question is from Pak Mazlan Madon. Yeah. Yeah. Mr. Mazlan, you can turn on your audio.
Thank you. Hi, Peter. Thank you very much for the presentation. I have one or two questions, perhaps. Well, I'm not a fan of the Hart curve anyway, but I just like to ask you about those diagrams you showed where you had the Hart curve against the geohistory curves.
Yeah.
I understand that they are two different in terms of magnitudes. They're very different. One is about maybe hundreds of meters, and the other is thousands of meters.
Yeah,
but I was wondering if we are comparing different things here, because the geohistory curve is a sediment accumulation curve. So it's a cumulative effect of tectonic subsidence and then sea level and whatnot. So even if the sea level curve fluctuations may be in the order of hundreds of meters, but the compounding effect of sediment loading and so on, incrementally will produce a very large subsidence in the order of kilometers. So
yeah, no, I agree.
That's one question. And the other one is, I'm not very familiar with Vim model. Bob is here, maybe he can also intervene. But my understanding is that model is also based on the observation that the main control is on the polar ice sheets. In other words, used to see. So how do you reconcile what you found in your years of looking at the stratigraphy in Southeast Asia?
Okay, two valid points. I'll deal them in the reverse order. The first few slides I did try to show that what I'm looking at is a scale of larger scale of stratigraphy. Bob is really looking at wells at high detail, looking for smaller scale floods to correlate in places like the Malay Basin, well, in a wide variety of sections. But he's looking for high resolution biostratigraphy. And I think he is seeing a signal there, but he has already said it's not the Hack signal, it's another signal. He's talked about possible links to the longest Milankovitch cycles. I think I counted about 32 of his Vim cycles in 30 million years. That gives you an idea of how high frequency they are. So yes, he's seeing something I'm tending to overlook because I'm looking at the larger units. And yes, you're very right about geohistory curves. Geohistory curves are an analysis that must be accompanied by supporting text. I can't do that in a presentation, but I do have supporting data for these because yes, there are other effects that do come in here. Sediment loading is slow and gradual, but you know when it happens. It's when the sediment accumulates. There's autocyclic switching, all these things. But what I'm showing on my examples, where you know at sort of the formation scale, large formations, like on this example, the cycle 4 limestone, that appeared very suddenly, very abruptly, and terminated very abruptly. And in this example, it had to have created that accommodation space. So that's pretty undeniable. Now, what happened in between? I hope the mouse is still working. Yeah. What happened in between? There could be little variations in here, but I can't see them on the data I have. And they're not really affecting the facies we look for. As this shallows up, it gets sandier. This is based on wireline logs, just simplified. And of course, the limestone is based on wireline logs. So at a crude scale, basically, we see one pattern. And yes, there will be longer term cycles for loading. And certainly the work that hopefully Sabin will come from his modeling, we'll see these epirogenic changes then. But these examples I'm showing have been selected to show this rapidity of sudden changes that switch on major changes in the basin changes shape. So I'm looking at a certain scale, which is why I'm not seeing Bob's high resolution section. It's probably in here. I'm sure Bob has worked on some of these wells and he can pick out some things in here. But I'm looking at a certain scale. It's about the scale you do play analysis at, risk analysis at, and we see it's controlled by tectonics. So again, when you draw these diagrams, you always keep notes on what the quality was, on how good your ages are, what the well next door showed, because like I've shown, wells next door can support and challenge each other. So again, they're ideal for a certain scale of observation. But no, I agree entirely, there will be other effects coming on. But nobody I know has ever seen the hack curve in Southeast Asia. You look at the big events. In fact, I've gone through a history from the big mid-Oligocene event. Hack has always maintained it, has changed its size a little bit, but Snedden and Liu from ESO in 2010, they don't see it. The work by, the name escapes me, Miller 2005, 2009, he doesn't see it. So you say that's a big one. Okay, the effects in about 10 million years. Again, no, what we see then is definitely tectonic. So again, we're just not seeing, there's no evidence for the hack signature. Bob is definitely seeing something of a high resolution, but a sort of the mid-resolution, which moves the base, moves the formations, it's clearly tectonic. But agree, we have to justify our geohistory curves with a background of documentation on what went into it, where there were sidewall cores, what was the quality of facies analysis, and maybe supporting seismic lines. Because you just can't churn out these diagrams to say this is what goes on. There has to be a data audit trail. And that's a key part of this evidence-based approach. It's not just declaring this is the answer. You've got to have that data audit trail if anyone's going to believe you. And that's why a whole bunch of documentation is going on and hopefully be published soon. So I can tell you something, and if you disagree, as I'm sure many of you will, hopefully you'll be able to look at my paper and see why I said that with what confidence. And that's unavoidable part of the evidence-based approach. But hopefully we'll go through a phase of that for a few years and get a new framework sorted out. But yes, you're very right about geohistory curves. They are wonderful tools, but to be used with qualification, not just blindly saying this a computer generated it, it's right. You have to explain all the error bars that go with it. All geology data is got error bars. They're based on proxies. You know, we rarely measure age directly. It's based on fossils. What quality fossils, all these sort of things, they need documentation. They should be open to peer review and criticism. But for the scale I'm looking at, which is about at the formational scale, these geohistory curves suit very well to show the major changes. I interpret this as a simple collapse because it happens so quickly, and you get on that on seismic, it might have a different gradient. So all of these things have to be explained, but it can't be any more or less than a certain amount. And within that, yes, you will see other effects. Bob Morley's VIM cycles will be in there somewhere. And there may be longer term epirogenic and sediment loading features in there too. This kind of smooths those out. So valid point, but I think it really is handled by how you document your geohistory work.
Okay, Peter, thank you very much.
Yeah, thank you, Pak Mazlan Madon, for the question. The next question from Bob Morley. Bob, you can turn on your audio, please.
Are we there yet?
Yeah.
Hear you.
Hello? Can you hear?
I can hear you, but I can't see you.
We can hear you. We can hear you. We can see you.
Ah. Well, maybe you don't want to see.
Right.
Not sure.
No, you'll just have to hear.
Oh, it's
Okay,
good.
go ahead.
It's good. It's okay. Yeah.
Okay. Well, it doesn't really matter if you can't see, but at least you can hear. Yeah, I mean, I've really enjoyed this talk, and thanks for Maslan sort of introducing the issue that I'll bring up now. And I mean, basically what we've been doing in the last couple of years with Petronas is to look really in detail at every stratigraphic interval, just to find out what the used to see signal actually is. And what we find is that the used to see signal is there wherever you look, but it's it's at the scale, as you would expect, of the global isotope curve that reflects through the Miocene, mainly Antarctic glaciation, as Maslan just introduced. When you get into the middle and later Miocene, then there are some other issues that that result in somewhat higher resolution cyclicity. But again, they're all very predictable, and they all fit with the pattern of the different patterns of isotope changes, whether it's oxygen or whether it's carbon isotopes. They are invariably always there. What happens is, you know, the isotope signals are there, the sea level changes are there, but they're at the scale of glacial-eustatic changes that have occurred during the course of the Cenozoic. And you can see this very nicely illustrated, say, in the paper that we just published last year on the Coulomb Basin, where you've got these, I mean, I was really surprised that it all fell into place. The Vietnam Petroleum Institute have done some really detailed palynological work in Coulomb, which was as if it was just waiting for me to go in there and sort this all out for them. Thousands of meters of lacustrine and fluvial successions with lots of cyclical lacustrine fluvial depositional patterns. Now, when we looked at this from a sequence by a stratigraphic point of view, we found we could determine about 36 cycles through the Oligocene and the late Eocene, and with the very few markers, but there's two really good markers, one at about 35 million and one at the Oligomycene boundary, and those cycles all had 395,000 year cyclicity, which is really the 406,000 year cyclicity that is very well documented. There's a nice paper in Science about 2006 that says 405,000 cyclicity, the heartbeat of the Oligocene climate system. So what we're actually seeing in Coulomb is exactly 405,000 year cyclicity is basically driving the local depositional cycles. But if we cross-correlate these across the basin, then we can see that the succession divides up into 5 packages, and those identify tectonically driven packages, nothing at all to do with climate. But the result is that they could be visualized as third-order sequences. And what you essentially see in Coulomb is a succession of 5 broad third-order depositional sequences driven entirely by tectonics, broken up into, depending where you are in the basin, between about typically sort of 5 to 8 405,000 year depositional cycles, which are entirely driven by glacial-eustacy. Now, of course, those cycles will be thicker in the basin deeper center, or where you've got more sands coming in, and thinner, or they may pinch out altogether at the basin margin, but they're essentially driven by glacial-eustacy. And basically the same pattern applies wherever you are, and that's what makes these so good for correlation, because if you can define them properly, which requires really good biostratigraphy, closely spaced samples, as we've seen in some places in the Malay Basin, in Sarawak, in Sabah recently, then you can develop a very high resolution stratigraphy. And if you linked that, integrated that with the scale that Peter is working at, I think we'll see some real surprises in how our sediments have accumulated in different parts of Indonesia and Malaysia during the course of the time that we're dealing with. So yeah, I think the cycles are there. The glacier used to see us there, but it's a finer scale than all of our hack people would like us to see. Now, in doing all of this evaluation, we have really we've got very little support whatsoever for hack. And we've just written this up as a paper. We want to get this published very soon. There are 4 major failings that hack can be in which it is possible to criticize hack. The whole hack scheme might have, it was an eye-opener 40 years ago when it was introduced in 1988 or wherever it was. But today, it really needs to be replaced. To use it in places like Sabah to identify stages of fans is just absolutely ludicrous. So yeah, throw hack out of the window. Even the ISC, the curve used on the ISC chart, the Harden bowl, we find so many issues with. It's just a slight refinement of hack and nothing else.
Yeah, it is, yeah.
So I think I've finished there. I wanted to see a new tectonic model for Southeast Asia, Peter. Where is it? Is that
it's in a very badly drawn Adobe Illustrator file. I keep wanting to move things when I get new ages, and CUDAT I want to do first because that's so important. Then I'll start going through and modifying my maps. Because what I'm looking at, you see, you get these maps where people have preconceived ideas of what's a basin, and they draw their little oval, but that's shifted through time, as we know. And you suddenly find areas have been unfashionable for exploration. You think, well, why? There's sediment there, there are oil seeps there, the Mangilhat Peninsula, West Java, there are 2 off the top of my head. And there's many more because people have sort of fallen out of exploring these areas. So I'm looking at a scale where we can join these different basins together with one large-scale tested stratigraphic model and start extending plays into areas we haven't even thought of exploring, like onshore West Java, some very poor exploration down there. There's lots of areas around that, like that around Sunderland. But again, ultimately, yes, we need to combine it with a high resolution scheme that really is there. But you one study area that companies dominated for 20 years, you move a few kilometers away to a different nation or different PSC history, and you can't join up their schemes. We have to get past that before we get any decent models done. But again, my biggest problem with the regional tectonostratigraphic model is the proto-South China Sea slab pull. I have to get rid of that. And I
can't see it.
So yeah, we'll wait for that.
That's my success. So, because I can't fit that in with what I see, I've drawn all my diagrams. I don't care, Borneo rotates a little bit. We've looked at the latest magnetic data, but it's that subduction of a slab under northern Sabah, all the implications that go with it, I can't fit in. So if I can convince Chris Morley, who's a very experienced person on this, that will be my acid test. And that's still ongoing. And I think then I'll have these diagrams finished and sorted out. Plus, as with geohistory curves, all the annotation that goes with it, because I've got to explain why I differ from a published age on something or different facies. Because there are many places that have been discarded as shallow marine, they're bathyal, I'm sure Bob knows of some. A famous formation, not famous, a formation in eastern Sabah called the Balung Formation, hardly described, it's coaly, so therefore it must be shallow marine, high TOC. It's full of bathyal fossils. So things like that need to be documented, sorted out. The entire subsidence and uplift of northern Sabah needs to be explained, all these kind of things. But yes, very soon I've got these maps, drafts in my book for North Borneo, but they extend all around West Sumatra, proving pretty tricky, so there's just lack of decent deep wells there. But I can interpolate a little bit, but they're nearly there. But it's been quite a slog over 10 years. And that will come up, I think, hopefully we get some new people investing and exploring here. And then we will tie everything together from the small scale to the big scale. We'll have a new climate model, a new tectonic model, sedimentology models. That's why I think it's a very exciting time. And it's all based on evidence-based approach. You don't assume an ideal model. You get your samples out, you analyze them, you look at the log, what the casing was. You get out the field reports. You do more field work. There's a sand called the Batu Blast sand at the north end of Sarawak, mapped in 1957. It's a turbidite. They've got an oil seep in it. When Conoco drilled a Lalawak well about 3 years ago, they had no idea this was an analogue for their play because it hadn't been revisited since 1957. I found one person who'd been nearby, stopped, got a sample, so I could verify some of the old mapping. That's quite easy access. And I've got a list. We can go through places that students or people can get into, do important new field work, confirm what I suspect, or do new work. Kudat, another good example. Maslin's already invited me up there next time he goes. Lots of new work to be done in Kudat that would firm things up. So we could have a very productive couple of years and trigger a whole new phase of investment and exploration in the region, because a lot of new ideas will come out of it. I've got some already. I've seen them on seismic 2D and a bit of 3D. We need to get companies convinced that this is real, why they were overlooked for so long, because people weren't fools before, they did good work, but why weren't they seen? And what are they worth in terms of risking now to go and explore? Because Banyu Urip, remember, this was 2000, they confirmed Banyu Urip, that's 20 years ago. More oil and gas has been found in the last 20 years in East Java than an entire century before then. A reverse creaming curve. That can only happen when you don't understand the geology. If you understand the geology, you get a normal creaming curve, basic statistics. I think that won't be the last time it happens. I'd love to know what happened about the Tarakan, Kutai, East Sabah area. That needs some more work on it. And we know that's prolific. There are seeps in the Eocene, in the Oligocene, of course, in the Martian Pliocene. Very complicated. I wouldn't say it's too complicated. You just need to do some simple work in the area. You could go around listing these areas, but you've got to do the work. You can't just shoot seismic and the answer will ping out at you. It won't. Seismic is invaluable, but I think we've neglected analytical work for 20, 25 years. And people like Sukarno, Bob, and the others have really got to play a bigger role in exploration. David Gull, CGG, get labs involved, fission track work, find a new way to do this work. Drop the price per slide mentality. That's been a very negative evolution, especially on work. You have to kind of live with it. I know probably you do, Bob, but there's got to be a better way to incentivize people to go and come up with new ideas, sort things out away from this simple price per slide damaging model. And I think we're close to it. We just need a final push. And like I said in my final slide, I think in the next 5 years, we're going to get something quite new for the area, tectonically, climatically, stratigraphically. All sorts of things will come out. We'll understand the sapphire garnets of sapphire alkaline basalts of Vietnam better. There are rubies on East Borneo. What the hell are they doing there? So there's all sorts of things coming out of this. We're stagnated. And we need to have a big push on analytical, evidence-based geology to get our way out of it. And at the moment, the next generation isn't really prepared for this. We have to explain why, make them excited about the geology of Southeast Asia. There's so much going on here. It's a fascinating place. I spent my entire career here without any regrets, and there's still a lot to be done. So I want to get the next generation excited about what they can do in Southeast Asia. And a few nice discoveries, I think, will bring the companies back in, and we could have a very good exploration phase for the next 10 years in Southeast Asia as a whole. And Southeast Asia, of course, everything changes, it's more active, but then the potential for big things like Walther are still there. So it really has been underplayed as an exploration and geological area for a long, long time. And I think it's thanks to a few people who hopefully can turn that around in the next few years.
That's true.
Yeah, very good, Peter.
Good, good, Peter.
Yeah, one thing I would like to say on that Peter has sort of brought to attention, things like the price per sample and the sampling interval is one that I find always remarkable. That as you increase the or as you reduce the sampling interval to say from in palynology, people used to look at samples at say 90-meter intervals, which was too wide. If you can reduce that down to very short time intervals, such as 10 meters, suddenly you see many, many events appear that you never ever imagined might possibly have been there. And so I would say in biostratigraphy in general, I've seen more new characters and more new features come out with high resolution closely spaced sampling than I did in the previous 20 years.
Yeah,
so there's lots and
that.
lots more to come out.
Well, I pointed out that F-19 well, they took 172 sidewall cores. BP did a well in Vietnam, and it's got one of these numerical names I can't remember. They took lots of sidewall cores and really analyzed the hell out of it. Great job. I think they just did one or two wells like that that interpolated. But great work like that. And we're just simply not doing it now because we can't justify it. Now, managers aren't bad people. There's some very, very good managers at Petronas and other companies too. You just need to go there and explain why you need this. And at the moment, there's so few people arguing this case that an easy way to save money, don't run sidewall cores, just do the minimum geochem and biostrat to keep me gas or NPM happy. I think the job is to convince them that no, do this work, it's background work, publish it, do something with you because the area will develop. And so I agree entirely with Bob. The cost of this compared to a few kilometers of seismic is tiny. It's simply convincing the managers that something good will come out of it they can defend to their managers.
Yeah. Agreed entirely.
Okay.
Okay. Okay, thank you, Bob, for the discussion.
Cheers.
Yeah.
I'll let you go to the next question.
Yeah, thank you, Bob. Thank you very much. I'm really happy to enjoy your discussion. Okay. The second one, the next one is from Hadi Maulin. There are two questions. First is, what is your opinion about Miocene delta in Tarakan Basin? Is it a common delta setting in passive margin or a delta tectonics in back arc of South China Sea? And the second one, how do we observe Miocene unconformity in Tarakan Basins? Since we found so many unconformities from early Miocene to Pleistocene, particularly in Parang to Padi.
I suggest you get in touch with me offline about this. I've written this up in my book on northern Borneo, which goes right around the margin. I'm doing a lot of review of the onshore work because it had been neglected, tied to the offshore. And I go across from East Sabah into Tarakan. I'm very familiar with the area, the lack of wells, and there's a lot going on there. I'm not going to try and go through it now without diagrams. It's controlled by strike-slip fault movement underneath. And you can tie that to movement in the Sabah orogeny and extension in the South China Sea, which is why I think they must be linked. It's too much to go into now, but basically you get the little pop-up limestones like at Pulau Fani, where this limestone, which is earlier Oligocene age, grows on top of Eocene bathyal clays, then it drops down to get bathyal clays on top of it again. So a lot of activity going on with wrench faults. Those wrench faults then develop through the Miocene, and then the sediment source changes through the Miocene. That's the critical thing. Which bit of the Miocene, the middle Miocene, late Miocene to Pleistocene? Because most people aren't aware, it's not in this talk. If you look at the onshore East Sabah area, on surface, you've got things like the Tanjung Formation, which is coaly with a few limestone interbeds, so at sea level, middle Miocene, and the vitrinite reflectance is about 0.5 to 1. So that has been buried. This is from burial because there's enough data points from a PhD thesis and some work Sun Oil did over a very wide area showing that area subsided, had about 2 kilometers of overburden that is no longer preserved. Of course, then it was uplifted and that overburden was taken away, and it's now up in the hills. That entire subsidence event and uplift event are undocumented. I've managed to tie that vitrinite. I just wish I'd done fission track work, but they haven't. But that vitrinite pattern I can tie to the development of the Kinabatangan Delta in East Sabah, and I think to the data in the Tarakan Basin, where you're getting pulses of the sands through there. Now, the trouble with the Tarakan stuff is each well is very poorly dated, because when a sand comes in, it's in such tremendous volumes, you're diluting the fossil content in a fluvideltaic sediment that's pretty poor anyway. So a little bit is estimated because we just lack the age control. Petrocore tried strontium dating. I've got that data. It's some success, but it's all controlled on the wrench faults and what happens in the hinterland source. So this will be published. The Geological Society of Malaysia has agreed to publish this, and I've sort of sat on it for years. I've been writing papers to get peer review on some of the important points. But this has been drawn up to moderate level. I'm willing to share this, but it's a complicated subject, those sands. And again, this is a time where you get 1 or 2 wells, pull them out of storage, reanalyze them for good quality age dating, which will not be easy. You have to structure your contract, not on a price per slide. So say, I've done 20 slides, job done. You might have to get a big sample just below casing and process the hell out of it just to get a few forams or fragments of strontium. So it'll be targeted analysis, trying to clarify the ages of these sand units, tie it to the tectonic history, hopefully get somebody to get a sample. They've got a new road across East Borneo, get a sample from there and do fission track, date the uplift a little bit. And we've got the framework, the loose framework of a new system. It won't take much to upgrade it and get a really good framework. But Tarakan is one of those areas you need to get access to the Saba data that's pretty good and merge the two together, and we still lack a few crucial well sections. But anybody with questions on that area, please get in touch with me. Within reason, I can't send you reams of data, but I can give overviews of stuff I've already drawn and annotate with questions and possibilities. It's just too much to try and pull up on screen now. But this is a classic area where a little bit more work. Access to the data that you didn't know was there across the border in Saba, this unconformity where you're getting the subsidence and the uplift. They're two huge events tied into your sand supply, your sediment supply, your accommodation space. That will resolve these problems. So I think we've identified the problems and an outline of the answers, but we need some pretty cheap, or some field work in the area would be superb. For northern Tarakan onshore, I was using Van der Vleut 1921 and 1929 because nothing more modern had been done. I know the Geological Survey has been in there, get their samples, do some work. So this is the classic case where a little bit more work would really resolve and change our view of the area. But I think we've got a good understanding of the major problems now, and I'm willing to share that with anybody who's interested. As I say, just get in touch with me through FOSI can give you my email. I'm not, if this is going to go on YouTube, I'm not going to give it now, but just get in touch with me and I can supply my sketches as they are at the moment. Okay, thank you, Peter. I think that's the question from the chat box. I've read it all for you. And then thank you very much. On behalf of FOSI, I'm very honored to have you. And this is a very insightful and very interesting presentations. And as I said before, and I will record this, and then later I will upload this to YouTube, so anyone who cannot attend this meeting can enjoy the meeting in YouTube. I think that's for me. I think Melinda, you can have time to close this session. Yeah.
Okay, Mas Ricky. Thank you, and thanks again, Peter. Basically, I have a question for you, but maybe later on I will offline. I will send an email to you.
Yeah, please. I do want to discuss this. There's people out there who've seen stuff I haven't seen. I want to start a discussion and keep it rolling, and hopefully we can get some funding to start knocking these problems on the head. I think we can now convince companies to start looking. So any questions, any comments, I'm looking for allies and people to discuss geology with. So send email.
Okay, yeah, so please allow me to share your email to them.
Anybody who asks, I say I don't want to put it on YouTube. I didn't put it on the presentation. You can find me on ResearchGate, on LinkedIn, or through FOSI, and some of you will know my email anyway. But yes, please get in touch. I want to start a discussion and get interest and excitement going about geology. Because like I said in the opening slide, this area is not mature for exploration, and there's a lot of new academic things that we can do for geology to make Southeast Asia a leading center for geology. It's a superb opportunity. There's a lot to be done here, lots to be done. So please, any questions, please send them in.
Yeah, okay. Yeah, many thanks, Peter. So yeah, at the end of our session, so later on, if we upload your video to YouTube already, I will let you know. And to all participants, thank you very much for joining us. I will share to you the presentation materials, and I believe Mas Ricky already shared the link to the chat box, and feel free to download the materials as well.